So how much should you charge? Humbly, 5 rows in this video. I am just hi everyone. Welcome to hi everyone. Well, hi everyone. We're back with hi everyone with Web3 AI. All right, guys. Hi everyone. So welcome to Web3 Complete Web3 Roadmap 2023, not roadmap, the bootcamp. Super excited for this one. It's been a long time coming. I was not in India for around 2 months, as a lot of you know. So this has been shot in a few places. I wanted to quickly give the structure of the whole video, how maybe you should spend time learning it, and what we've learned in this one, what we're learning in the videos to come. With that, let's get right into the video. So what's coming is specifically for this module, we have total 5 parts. All of this is on GitHub and all of this is on the internet. I would urge you to code along with me throughout the video, throughout the 4 or 5 hours that are coming, so that you also learn and don't get stuck in tutorial hell. The first 4 modules are us understanding Solidity, which is like the popular language used for smart contract development. Before that, I tell a little bit about what are smart contracts, what is Ethereum, and how you can deploy smart contracts there. Mostly the goal for this first one, which is extremely beginner friendly, might feel very slow. That the goal is for it to be slow, simple, and for everyone who's come here to complete it. Very beginner friendly, straightforward. Feel free to go to X, feel free to just make sure you complete it. And if you don't want to spend time learning, which is the first 3-4 hours, you can also finally skip to the assignment, which is the us building our own payments project in Solidity. Okay, so the first 4 parts are actually going through this very famous website called Crypto Zombies and me solving the assignments there. It's a very nice way to learn the basic syntax of Solidity. That's what this part of the bootcamp is going to be. You can either go through that yourself, you can watch me do it, you can put me on the side and put yourself on the side of Crypto Zombies and solve it along with me. The 5th part, building our own contract, is the most interesting bit, the place where you're going to choose some glass, understand how you deploy your own contract, understand how you can accept payments from other people, how you can create front ends for it, and deploy your own centralized backend which listens on the contract. That's the most, what I would call a practical implementation of what we've learned. So at least do this very best, do everything, and throughout this journey for the first 4 parts, things will be fairly straightforward because we'll be writing everything in a code editor. 5th part, you have to install a wallet, backpack, MetaMask, maybe put some ETH in it as well if you actually want to deploy the contract, and understand how sort of the deployment happens, which is the most difficult bit. Not difficult because of the contract. If you've done everything from here to here, 5th part should be straightforward for you to implement, but actually deploying it requires you to buy some ETH, which if you're in India, it's hard to buy ETH and like get testnet ETH as well. So you might not be able to actually deploy it. I would urge you to, choose some glass, go to a centralized exchange, try to buy some ETH, send it to your non-custodial wallet, backpack, MetaMask, and then over there, try to actually deploy a contract on the testnet, on the mainnet, does not matter. That is when you've learned, you have something to show, yada yada yada, you get that dopamine hit of creating your own contract and deploying it on Ethereum. Cool. That is the high level structure. Short in a few places might feel haphazard, but the goal is for us to go very slowly, and me solving Solidity again, which I did a few years ago. So it was a learning experience for me as well. Hopefully it is for you as well. Try to complete this one. I think in the next 2 to 3 weeks, we'll move on to the next video. This is a long series. The second part is going to be us diving into some real world contracts, especially finance based like DeFi contracts that hold a lot of value today, like millions and billions of dollars on the Ethereum blockchain. In Web3, it's very easy to get distracted and build like random use cases that no one wants. This is why the use case that we've built actually has a real world utility of buying my course. So this finally thing sort of, the thing that I've built especially will teach you a bunch of things, but for me it has some utility that it allows people to buy my full stack course. It's always a good idea to build projects that people want, which is why in the next one, we're going to read projects and understand the smart contracts that are currently being used on the Ethereum blockchain, the most popular ones. Cool. After that, the 3rd video is going to be Solana. The 4th video is going to be cross-chain deployment, which means sending assets from one blockchain to another. That's probably where we'll try to cut a line and then understand where we have to go next. But that's what the first 4 videos are going to be. Each one of them is going to be 3 to 4 hours, and hopefully you learn something new. And let me know the feedback in the comments. I'll see you guys in the next one. Bye. happening, and I'm going to be releasing a bunch of videos on how you can start writing your own smart contracts on Ethereum, on Solana, how you can make smart contracts move from one chain to another, basically a bunch of advanced things. But before we get there, we should start slow, and that's what this video is going to be. This is week 0 of the complete Web3 Bootcamp. In this video, I'm going to take you through the basics of writing a smart contract in Ethereum, what Ethereum is, what are smart contracts there, and how you write them. We'll basically understand the complete syntax of writing most Ethereum smart contracts. So you should be well versed enough to write a contract of your own. Once we've done all of this very theoretical, you following me coding, I will put out a problem and urge you to code that problem yourself, create your own contract. If not, I will also be creating it in the second part of the video. Finally, we will deploy it on the internet, and you can understand both how to write a smart contract and how to create a website that can interact with the smart contract. That's the end goal. But before we reach there, I have 4 modules for us to cover, which will cover the basics of Ethereum. Before we do that, let me quickly give you a brief of Ethereum, although I have a very long video where the first 30 minutes I just rant about what Web3 is and the history of Ethereum and Bitcoin. You can go and check that video out, or you can just stick here for the next 5 minutes and I'll take you through the basics of Ethereum. So what is the structure of the video going to be? Basics of Ethereum, what are smart contracts for 5 to 10 minutes. 4 modules of us learning Solidity from basics to medium, not advanced, but like fairly medium. Then us writing a smart contract of our own, specifically the smart contract that does some Web3 things, lets you do payment, but also does some Web2 things. Finally, we will create the front end for this. Before that, let's get right into the video and start with the basics of Ethereum. Cool. Let's do it. So the first 5 to 10 minutes, we're going to discuss this blockchain called Ethereum. Again, there is a very long video where I've discussed this. You can go there. If not, this is a quick reminder. Ethereum was one of many blockchains that came after the OG BTC Bitcoin blockchain. What is a blockchain? It's effectively a network of computers that talk to each other and secure a network. What does securing a network mean? In the case of Bitcoin, it simply means it contains an addressing from a Bitcoin address to how much Bitcoin they own. It is actually a very, very long ledger which contains who has how many Bitcoin and how they got transferred between accounts. And finally, by the end of it, you can calculate what account has how much Bitcoin. That was the initial use case of Bitcoin. The best part of this, or the innovation that happened here, was without any central authority, with a bunch of miners all around the world, with some incentive of them being able to mine Bitcoin, you can create a secure financial system. What was the problem here? The problem was, one, it only does one thing, which is financial transactions, and more importantly, only does one type of financial transactions for a specific token or currency, which is Bitcoin. It doesn't let you do a bunch of other things. To solve this, a bunch of other blockchains came, and Ethereum ended up being the winner amongst these. What did Ethereum introduce? It is the same thing. It is a network of computers, and they maintain a ledger of who has how much ETH now. But there is one other thing they let you do. They let you deploy smart contracts on the blockchain. So if you are a programmer, you can write some code and deploy it on one of these machines, well, multiple of these machines. What happens when you deploy this code on these machines is that other people all around the world can interact with this smart contract that you have deployed. And whatever your smart contract does, these people are able to leverage that code that you've written. What is a practical example of this? A very practical example of this is Ethereum was the first blockchain that let anyone create a token of their own. So ETH is the native token, but Dogecoin is a token that actually exists on the Ethereum blockchain. It is actually a smart contract that someone wrote, which simply said person 1 has 100 Doge, person 2 has, let's say, 20 Doge. And anytime people interact with this smart contract, they can either convert from ETH to Doge, let's say, or Doge to ETH. This has a bunch of logic that is very pertinent to a coin. What are the properties of a coin? Things like there is a limited supply of a coin. That's the same as currency. For example, INR, there is a limited supply and two people can exchange it for goods and services. That is true for any coin throughout the world. And so you can actually create your own coin similar to Doge, similar to, I don't know, some other random shit coin, Shiba Inu, and deploy it on the Ethereum blockchain. That is one use case of a smart contract. Seems like a very weird, ganda use case. So let's move on to another one. Another very famous use case of smart contracts is a decentralized exchange. From the very top, what is it? It is a contract that lets people swap Ethereum for USDC or Ethereum for Bitcoin, let's say, for example. It is basically a contract which somehow, don't worry about how, but somehow, if I have, let's say, 10 USDC, if I call this smart contract, it takes my 10 USDC and gives me back 0.0001 ETH. All of this is not natively written by the people at Ethereum. Similar to how Bitcoin only supports transactions of BTC, Ethereum only keeps track of, in terms of currency, the transfer of Ethereum and which account owns how much Ethereum. They don't really know/care about other currencies, the Ethereum core blockchain. But you can write your own smart contracts that let you introduce coins. You can also write your own smart contracts that let people swap coins from one person to another. Cool. This is one of many use cases of a smart contract. Specifically for us, as I said, today we are going to deploy a smart contract on this Ethereum blockchain such that anytime someone interacts with this smart contract, they can send some ETH to it, let's say 0.01 ETH, and this will emit an event which will be caught by a centralized server, and it will create a meeting, Google Meet schedule between me and them. How? We will come to. But this is, again, a nice use case compared to a Web2 use case where we have a server on AWS. You can just, well, there are a bunch of hoops to go through. You can't directly send me money through UPI in a programmatic fashion unless you're using something like Razorpay or Stripe. This is a highly regulated industry. Banks don't give out APIs to anyone in the world. They give out APIs to some centralized authorities like Razorpay, Stripe, and then they create a very nice user-friendly APIs for all the people in the world to use. The problem here is, again, there's a boot up time. They do a lot of verifications, which is good. It should happen, and like there is a reason it happens. But if you want to quickly like exchange very less 0.001 ETH for an event like this, Ethereum lets you do it because people can, without any central authority, without any bank, without any regulation, which I'm not saying is the best thing in the world, but it is possible to send some asset here in lieu for some service, which in this case is a video call with me. Cool. That's one of many use cases of these things called smart contracts. If you need a broader overview, you can go back to my original Web3 roadmap and you can see it for the first 30 minutes. If not, hopefully this was clear. Now let's move on to how you can write smart contracts on Ethereum. Every blockchain has its own sort of stack to write a smart contract. Ethereum specifically introduced a new language called Solidity. So just like when you're writing browser code, when you're writing front-end code, you write your code in JavaScript, you write your code in React. On backend, you use Rust, you use Golang, you use Node.js. If you want to write a smart contract and deploy it on the Ethereum blockchain, you have to use this new language called Solidity. You have to understand this Solidity. Why a new language? That's what the Ethereum folks decided. Okay, we need a new language. And this is a very sort of contract-centric language. So if you want to create this thing called a smart contract, it gives you the right constructs for it. Cool. For the next an hour and a half or so, we are going to do this. All right. So for the next hour or so, we are going to first go through 4 modules, 1, 2, 3, 4. The first module, we're going to understand very basic syntax of Solidity. How can you write a contract? How can you write functions? How can you write variables? What are scopes, public, private? If you're from a Java background, you already know this, or even C++. How to do hashing or random number generation in Solidity. Once you've done that, what is a view, what is a pure function, and basic arithmetic, which is like plus, minus, modulus, things like these. Oh, did my pen just die? That's fine. Yeah, it did die. That's all good. The second part, we're going to, let me zoom in here, understand this thing called cross contract calls, which means how one contract can directly call another contract. You don't necessarily have to call it from a browser. If you call a contract which will call another contract, think of it being very similar to a website like Udemy, where you pay, but the payment actually goes from Udemy's server to Razorpay servers, and then the finally payment is confirmed, and then they get back a response and it comes back to you. Okay, one smart contract can call another smart contract. How? We will see here, and a bunch of other things. In the third part, we're going to understand how you can optimize your contract. This basically means how you'll understand where does gas go, what is gas, why is it always said that Ethereum is very expensive, and any interaction that you want to do there, you have to pay money, and how you can optimize your smart contract so your end user doesn't have to pay a lot of money. Finally, point 4 is payments, which is very important. The biggest use case of Ethereum is that you can transfer ETH when you're calling a smart contract. If you remember a few minutes ago, I said you can create a smart contract where I send some ETH, I get back some Doge. I send some Doge, I get back some ETH. So you can not just call functions, you can also send tokens or send Ethereum when you're calling a function. How you do it, we will understand in this module. These 4 modules are enough to understand the basics of Solidity. Once you've done that, we will move to creating our own calendar contract where, as I said, you can call a function and send some ETH with it. When you do, somehow a Google Meet link gets created as a calendar invite between you and me. Once that's done, we'll also write the front end for it in React. So you'll understand how once the thing is deployed on the Ethereum network, how you don't need a backend of your own. You don't need to have a Node.js backend. You can simply always just interact with the Ethereum blockchain to do things like creating a meeting between you and me, just calling the contract directly rather than a centralized server in the middle. So you don't need AWS, you don't need GCP. There is a network out there and you simply interact with the network, do function calls there. Cool. That is going to be the high level structure. Let's get into module 1, which is basics of the language. So at this point, I would urge you to go to cryptozombies.io. This is a website that makes it very easy for you to understand Solidity. I will be solving all the challenges here, and that will be a way for us to learn. I urge you to do it side by side or just close the video and do the challenges yourself. Either way, this is probably the best resource to understand the basics of Solidity. Extremely beginner friendly, and it sort of gamifies the whole experience. The only downside is it's a very weird sort of a use case that they make you build, that they make you write the contract for. So it might feel a little weird as to why we're writing this contract, but the goal is not to write a contract. The goal is to understand Solidity. Cool. You can go to cryptozombies.io and I would urge you to sign up. You don't have to, but it like gives you a bunch of pop-ups throughout if you don't sign up. So I just sign up. I'm good. Alrighty. Once you do it, you will see a bunch of courses. The courses that we will be going through is 1, 2, 3, and 4. These are the 4 modules that I just discussed. And these should make you enough, like decently proficient in Solidity for you to be able to write your own contracts. Cool. Let's get into the first one. As I've said, this might feel a little weird, so just bear with me for a few minutes. And once you start writing code, this will become slightly easy. Cool. Chapter 1, the lesson overview. Oh shoot, am I sharing the right thing? I am not sharing the right thing. We will restart. So I just said 2 things. The first thing I said was go to cryptozombies.io and you can basically follow along the challenge. Start coding with me. It's always good to code yourself and not look at someone else. If not, feel free to just look at me and passively watch me learn Solidity for the 4th time. I've done this a few times now. Cool. This has a bunch of challenges. Specifically, the one that we need to go through today is the Solidity challenge. So if you go to cryptozombies.io, go to the courses section. It's completely free. And my internet is a little wonky today. If you click on the Solidity beginner to intermediate smart contracts, that should take you to the first thing that we're doing today, which is this guy right here. Click on start now. It has a bunch of modules. We have to do the first 4 modules, and those should be good enough for you to start writing the contract that we have discussed. Cool. Let's start with the first one. The first module, so this is the point where things might feel a little weird, but bear with me for some time. What we have to build here is a game. You might ask why on-chain games. I would say just bear with me. The goal is to understand Solidity. So this is a weird use case that we're building, but on-chain games are a thing. But yeah, you might feel why. I feel the same. Cool. What does it say? It says you're going to build a zombie factory, which is what our contract is going to be, to build an army of zombies. Compare it to a game where there is a game, Web2 game, where you go to zombies.com and you can create a zombie of your own there. You sign up, you get back a zombie. Cool. So you're creating a game rather than there being a centralized backend. It is running on the Ethereum blockchain. How? We will come to. Our factory will maintain, now what is factory here? It's just a game. Think of it like a game. Our game will maintain a database of all zombies in our army. So if on a Web2 website, 100 people log in some database, there are some 100 users and each of them have a zombie associated to them. Similarly, we have to do the same thing on chain. Our factory will have a function for creating a new zombie. In the Web2 world, this is simply you signing up and maybe clicking on a button that says create a new zombie. Cool. When we finally create the front end for it, we create the front end for it, we won't in this video, but if you want to, after you've deployed this, you can create a website where there is a button, person clicks on the button and a new zombie is created for them. Each zombie will have a random and unique appearance. So this is slightly important. When you go to a website, let's say a Web2 game that lets you create zombies, you might get a unique zombie or you might expect a unique zombie from the backend, which is your character basically. Question is, how do you describe what the character looks like? A character could have some characteristics, which is like the head it has, the eyes it has, the shirt it has, the skin it has, eye color, and the clothes it has. There are a bunch of permutations and combinations of these which will create a unique zombie. Question is, how can you describe this in the simplest format so we can store it on chain? You could either have like 7 different variables which are like head gene number 1, eye gene number 2, shirt gene number 3, and you can store these as different variables in your database in a Web2 world, in the Web3 world, in your contract. Or you can have a single very long number such that the first 2 digits represent your head, the next 2 digits represent your eye, so on and so forth. Okay. You might ask, Sir Kirat, there are only 7 head genes, which is why if you have a DNA, you can simply say the head is the first 2 digits modulo 7. So if 83 modulo 7 is 0, that means this specific zombie has this sort of a hat. If it is 1, then it means this. Or if you want to do it on a 1 based indexing, if 83 modulo 7 plus 1 is 1, then you have this hat. If it's 2, then you have this hat, so on and so forth. Similarly, the next 2 digits represent the eye that they have. The next 2 digits represent the shirt that they have, so on and so forth. So effectively in a single number, you can store the shape of your zombie somewhere. So if you had a Web2 website, you can simply ask the user to sign up using username and password, email and password, and you can randomly generate a very long, whatever this is, like 16-digit number. And based on the 16-digit number, the appearance can change on the front end of your game. The game will simply calculate what the zombie looks like based on this DNA. So this very long string, the DNA, is a nice way for you to represent the Web2 in a very simple format that can be stored on chain versus you storing, okay, the head is of type black hat and the eye is of type chashme or a specs, so on and so forth. Cool. So what have we understood in this module? We have understood that these guys say we have to create a contract that lets users create zombies, and each zombie is identified uniquely by a 16-digit number. So maybe we have to randomly generate this number. What happens if 2 people get the same zombie? We'll get to it. Don't worry about it just yet. Assume that won't happen. And like our random generation is random enough so that even if 10 million users hit your website, each one of them will have a unique zombie. Cool. Let's move on. Chapter 2. Contracts. So here is where we understand how you write contracts. Think of a contract or the code that you have to write here. So there is a coding section here where you can write the code. There is a check answer button here, and there is a question on the left. This is similar to lead code. There is a question on the left. You have to code something and click on check answer. If it is right, it will give you an AC, else it will give you a wrong answer. The first thing it asks us to do is create this thing called as a contract. And if you read through it, it says Solidity's code is encapsulated in contracts. A contract is a fundamental building block of Ethereum. You can think of it very similar to classes in Java or JavaScript or structs in Rust. they basically let you store a bunch of data and have a bunch of associated methods. That's effectively all a contract is. Now there are some specific things that Ethereum has, which are like, you can store Ether in the contract, and it has some more things and specific things to the blockchain, which make their functions variables slightly different, but more or less what is a class in C++ is almost what a contract is in Solidity. So what have we learned? In Solidity, most of the times when you're writing code, you're creating a contract and writing all your code inside the contract. How do you create a contract? You simply write contract, the name of the contract, for example, hello world, and then bracket open, bracket close. This is similar to class hello world, and then this in Java or JavaScript. Alrighty. It also has very nice comments. It says create contract here. What contract? We just have to look at the thing on the left. Okay, let's see. Put it to the test. To start creating our zombie army, which means our game finally, or the contract, let's create a base contract called zombie factory. So that's what the name of our contract needs to be. Second thing it says it is in the box to the right, make sure your contract uses Solidity version between these two. So whenever you're writing Solidity code, at the very top, you have to define what version of the Solidity compiler it should use. Solidity keeps on improving as a language. This is similar to how TypeScript or JavaScript, Node.js keeps on improving and has a bunch of versions, ES 2016, ES 2020. So does Solidity. Whenever you're writing a contract, if you are calling a function that's only available in, let's say, in 0.9.0, you have to describe that at the very top. In our case, they ask us to simply use the version between 0.5.0 and 0.6.0, because all the functionalities that were introduced in this compiler is what we're going to use in this specific contract. In the future, if you write very advanced contracts which use new constructs that were, let's say, only introduced in 0.8.0, you can just change the title and tell Solidity, okay, use this compiler. Cool. But for our contract, it says it should be between these two. So what have we done? 2 lines we've added. Create an empty contract, and at the top, describe what version should Solidity use when you're compiling. Now we'll click on check answer. A bunch of times throughout this video, I am going to give the wrong answer because I'm writing this very fast and it's very late and I'm also very dumb. So when that happens, we can either look at the solution, although I will try my best to not look at the solution and solve the problem myself. Check answer and it looks good. If it looks good, you will see this victory sign, else it will tell you there's a wrong answer. Cool. Moving on, we've written an empty smart contract. Let's see what happens next. States and variables, integers. Standard. Every language has integers. How do you write them in JavaScript? Well, in JavaScript, you simply write them as const a equal to 2. How do you write them in TypeScript? Const a colon number equal to 12. How do you write them in C++? Int a equal to 2. How do you write them in Solidity? More specifically, where do you write them in Solidity? If you have a class, your class could have member variables in them. For example, if in JavaScript I describe a class called zombie, it could have a name variable which is a string, and then I could simply, whenever I create a zombie object, I could do zombie.name. Similarly, at the very high level, your top level contract could have a bunch of variables which are usually like global variables for your contract, and that's what they ask us to define here. This is how you define it. If you want a uint, which means an unsigned integer, this is the syntax that you use. Uint, whatever the name of your variable is, and then equal to 100. One very important thing it says here is this will be permanently stored in the blockchain, which means whenever this contract is deployed, it isn't yet, but whenever it is deployed, this gets stored on the blockchain permanently forever. And so you should be careful that if you need uint 64 or like a very big integer with like 64 bits, only if you need it should you use it. If you need a smaller 32-bit integer or like a 16-bit integer, that is what you should use, because the bigger the thing you're storing on the blockchain, the more money you have to pay when you're initializing the contract. For now, what does it ask us to do? It says our zombie DNA is going to be determined by 16-digit numbers. Let's declare a uint at the top called DNA digits and set it to 16. So what does it say? It says our zombie factory will have 16 digits. You might create a cat factory in the future which only has 3 DNAs, let's say. It only needs 6 digits. So based on your needs, your number of digits on the DNA might change. Ours is 16, and hence we're going to define that as a global here. You don't need to, wherever we are using DNA digits throughout the contract later on, you could have simply written 16, but this is a good, nice way to abstract a global variable. In the future, if you want to change it, you can simply just change it in one place versus changing it in 10 different places. Alrighty. Check answer, victory. Let's move on. Next thing it says math operations, and you might be understanding as to why this is the right time to introduce this. Math in Solidity is pretty straightforward. The standard plus, minus, into, divide you can do. The important one, or two important ones here that you need to know is modulus, x modulo y. This is also very common in other languages. For example, you could simply do DNA digits plus, don't do it here, you have to do it inside a method, but you get the idea. Plus 5, minus 5, modulo 5. And the important one that we need here is 2 to the power 5. So what is 2 to the power 5? It is 2 into 2 into 2 into 2 into 2. So this and 2 into 2 into 2 into 2 into 2 are the same thing. This is just an easy way for you to do a to the power b in Solidity. Why do we need it? Put it to the test. It says create a unit named DNA modulus. Okay, DNA modulus. It should be set to 10 to the power DNA digits. Why? Can you think about why? Let's go to the iPad for this. We are eventually going to store a bunch of zombies on chain. Each zombie, as I said, needs to be represented by a 16-digit number. Okay. How do you create a 16-digit number? You can create a very long number and then simply modulo it with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Any number modulo 10 to the power 16 is definitely going to have 16 digits or less. This is the reason we store this in the contract, so that in the future later on we can simply do whatever random long number we generate modulo 10 to the power 16. Hence it is a good idea for us to simply store it where? Here as a global variable. All right, moving on. Until now we understand how to declare integers. We understand how you can do basic arithmetic. Next up, structs. What are structs in Solidity? Similar to you could say objects in JavaScript, similar to structs in Rust, similar to classes in Java. They let you put data together. And why is that cool? That is cool because if you have a person in the future, or in our case we have zombies, and zombies could have names, they could of course have a DNA. If you did not want a DNA, they could have a hat color, eye color, so on and so forth. And rather than storing them separately, it's a good idea to just merge them together in a single variable type. So this is common across languages, not really specific to Solidity. They've just used the struct variable, which means a structure, and Rust uses almost the exact same syntax to create structs. So you can use almost the same syntax in Rust to create a struct. But if you don't yet understand struct, hopefully you understand objects in JavaScript. So where a user equal to name Harkirat age 21. This is the same thing. It lets you structure data together, which is multiple key and values together in a single variable. This is a person struct. Put it to the test. It asks us to create a struct called zombie. Syntax is simple. Struct zombie. Our zombie will have two properties. Nice. It will have a name, which is a string, and it will have, it will have a string name, and it will have a uint DNA. Each zombie will have a name and a DNA. And I think that's good enough. You have just described the struct yet, which is similar to creating a class. We haven't yet created objects of the class. We haven't yet instantiated any object for this struct zombie. We've just defined what it looks like. Cool. Check answer. We're good to go. So where are we? Understand variables, understand contracts, understand arithmetic, understand structs. Finally, arrays, again, very common across languages. This is how you define them in Solidity. String, the length of it, and the string array. You can also have dynamic arrays. They can keep growing in size. This is how you generate a dynamic array. Can you think of why and we need it here? What variable, what array would we need in this contract? Take a pause if you want to hear, but I'll give you the answer. You have to store all your zombies in an array here. Now, at this point, something weird has happened. Something new has happened that we've not seen in other programming languages yet. In other programming languages, when someone creates a new zombie, let's say you have a Node.js backend and you have a Web2 game, someone creates a new zombie, it gets stored in a database. Here, that doesn't happen. Everything is these variables. You can create a dynamic array here and you can just keep shoving objects here and they will always stay on the chain. You don't put them in some SQL table. You don't do this. If this is your backend, it doesn't interact with another blockchain, another database. it is your database and your backend. It stores your data. It does store your code for execution as well. Both of the things are directly stored here in the contract. And this is very different to how things happen in the Web 2 world, where you don't really store data on your backend process. You store it separately in a database. That is not what happens here. Here, you store everything in the contract itself. Cool. Let's see what it asks us to say. Also tells us public arrays versus private arrays. You can declare an array as public and Solidity will automatically create a getter method for it. The syntax looks something like this. Okay. Person empty array. If you write public, Solidity will automatically create a getter method for it, which means whoever is interacting with the blockchain can actually get the value of this public variable. Other contracts would also be able to read from it, but not write to it. So this is a useful pattern for storing public data in your contract. Okay, sounds good. Putting it to the test. Create a public array of the zombie struct and name it zombies. Okay, first thing we have to put here, like they've put person, we need to put zombie array. What is the name of it? Zombies. And is it public? Yes, it is. So we have created a public array called zombies. What is the type of it? It is a type of the capital Z zombie array, which is this struct right here, an array of zombies. Currently it is empty. When you deploy the contract, it will be empty unless you initialize it in the constructor. And then as people call your contract, more zombies will be shoved into this zombies variable. Let's check the answer. Seems to have worked. Function declarations. A function declaration in Solidity looks something like this. This is literally seems like the last thing. After this, we're good to go. What is a language? A class. We have that contract. Bunch of member methods, or sorry, not methods, variables. We have them. Arrays. We have them. And finally, methods. The last thing. This is how you write a method in Solidity. Function, the name of the function, and then the arguments. What do arguments look like? String. We'll come to what this memory is. The name of the argument and uint and the name of the argument, whether it's public, private, whatever. And then finally your function body. Okay, this is how you create a function. Again, only when you write it will you get comfortable with the syntax, but this is very similar to JavaScript. Function, the name of the function, and then variables. Only in JavaScript you just have the argument name. If you're using TypeScript, there's a slightly different syntax, but generally this is the type and this is the name of the variable. What this memory is, we will read through. The function is called eat hamburgers, which takes 2 arguments. For now, the body of the function is empty. Note that we're specifying the function visibility as public, which means people can call this function on the smart contract. This is similar to the final function that we will create, which will be schedule a call with Kirat, which will be a public function. People call it, send it some Ethereum, and a call will be scheduled with me. Cool. This is required for all references types such as structs, arrays, mappings, and strings. Mappings is one thing we don't yet understand. We understand arrays, structs, and strings. What we're also providing instruction about where underscore name should be stored in memory. So what is this memory? We're also providing instructions about where name should be stored. So whenever you are writing an argument, you have to tell Solidity where it should be stored. What do I mean by where it should be stored? This is required for all types such as array, structs, mapping, and strings. If you have any of these types as an argument, you have to tell where it should be stored. You can either store it in memory or someplace else. Let's see what those places are. What is reference type, you ask? There are 2 reference types that you can pass in an argument: by value and by reference. This is also a very common concept across languages. In C++, you might have heard of this. Whenever you're calling a function, you can either create the copy of the thing that you're passing in as an argument, and that copy is sort of passed through the function body, or you can give a pointer to the place where the variable is stored, so that the same variable that's being passed in is the same variable, at least in memory, that was present before the function was called. By value means that Solidity compiler creates a new copy of the parameter and passes it to your function. So if there is a function and there is an argument here, arg1, whenever I'm calling this function, let's say I have a variable a equal to 2 and I call x with a. If I call it by value, I create a copy of a and send it here, which means if this function actually changes a, it won't reflect here, whatever arg1, if I change arg1 here and I console or whatever, print a here, the value of a won't change if it is passed by value here. If it is passed by reference here, the value of a will change. So what are the 2 ways you can send a variable? Either by value or by reference. What is the difference? If you send it by value, what you're sending in is a copy, and hence whatever changes you make to this argument here won't reflect outside, else they will. by reference, which means that your function is called with a reference to the original variable. Thus, if your function changes the value of the variable it receives, the value of the original variable changes, which means if you ever pass, let's say there is a string, there is a struct here. If you ever pass a struct by reference and you change it, it is changed on the blockchain forever. If you pass it by value, it won't get changed. Note, it is convention but not required to start a function argument with underscore. So you can not use underscore here, but the general convention is that all the argument names starts with an underscore. Cool. Let's put it to the test. Let's create a function. So let me just revert all the things I added. Let's create a function which is a public function and name it create zombies. So function, name of the function, create zombie, arguments, it is a public function, and finally open braces and closing braces. What are the two arguments it takes? String, memory, name, and uint DNA. Cool. String, memory, name, uint DNA. Syntax looks right. Until now we have a streak. We have not submitted a wrong answer, and hopefully we don't hear either. Yep, good to go. What do we know now? Show me the answer again. Why does this not go away? Yeah, okay. So this was the syntax that we wrote, which is function, name of the function, and the arguments it takes. So where will this function be used? This is a public function. People on your website, if you deploy this contract, will call this function, and when they do, a new zombie will be created for them. That's the logic we have to write here. Working with structs and arrays. Creating a new struct, very important. Until now, we've only defined the struct. We haven't yet created one. The way to create one is this. Name of the struct. Name of the struct. This is the type of the struct. Name of the struct equal to type of the struct, and then in the arguments you give all these keys. Cool. The other thing it says is how do you push to an array? Fairly simple, similar to JavaScript. Call push and then push in the argument that you want to push to the array, which if your people array is of this type, what you will push inside is a people's object. If this was of uint type, then you would push just an integer here, so on and so forth. Why is this useful for us? Because we have to complete the create zombie function. Anytime someone calls create zombie, what do we have to do? We have to create a new zombie. So zombie equal to zombie underscore name comma underscore DNA, and then we have to finally push it to the global zombies variable, which is this guy right here. This is probably the two things it asks us to do. Fill in the function body to create a new zombie and adds it to the zombies array. The name and the DNA are already in the arguments. Let's do it in one line of code. Okay, sounds good. So I'm going to just copy this, cut this actually, paste it here and remove the line. Zombies.push zombie underscore name underscore DNA. So right now, whoever is calling this function can send their own DNA, which means we're giving the user the power. Eventually we will optimize it. For now, whoever calls this function can simply pass in a DNA and we create a new zombie for it. Cool. We understand functions. We have also completed the body of a function. Check answer, good to go. Private public functions, cool. Nothing straightforward. We had a public function here. It can be a private function as well. What is the difference? In Solidity, functions are public by default. Obviously, this isn't always desirable. You want to make some functions private so that they're not vulnerable to attacks, so on and so forth. This means only other functions within our contract will be able to call this function. Okay. If you make it private, if there is another function here, that function can call the create zombie function, but someone from outside the world can't call this function in your contract. Very useful. You want to structure your project into multiple small functions. You don't want the end user to be able to call all of them. The ones that you want the end user to call, you will make them public. Rest you will make private. Cool. Let's put it to the test. Our contract has this function which is public by default, which means anyone can call it. Let's make it private. Why? Because we discussed this in the last module, like just the last section. You don't want to give the end user the power to select their DNA. You want to randomly generate a DNA for a new user. The user should simply say create zombie, and then we should randomly generate a DNA for them and create a zombie for them. Cool. So we've made this function private. Hopefully it works. It doesn't work. For the first time, it doesn't work. Our contracts function is currently public by default, which means anyone can call it. Let's make it private, modify, create zombie. It's a private function. Don't forget about the naming convention. All private functions should start. It's a naming convention, so you don't have to follow it, but these guys make us follow it. They say, if a function is private, just start it with underscore. This is also a practice that's used very heavily in JavaScript. Done. Next chapter. More on functions. In this chapter, we're going to learn about return values. A function can return something. Any language, most languages do it. This is your function. Just add a return statement at the very end. Important thing to note here is this section added at the very end. So you have to specify what your function is returning. If it's returning a string, this is the way to describe it. If it's returning a uint, you will say returns uint, so on and so forth. In Solidity, the function declaration contains the type, which is basically this section right here. Function modifiers. In the above, function doesn't actually change the state of Solidity. Example, it doesn't read or write anything. If there is a function that takes, let's say, takes nothing as an input, but reads this greeting and it returns it by value. Memory is by value, right? Solidity, memory by value or reference, question mark. Memory means by value, most probably. Assigning memory or storage by reference. Yes, storage is by reference. Memory is probably by value, which means this guy is just returning greetings by value, basically creating a new copy of it and returning it. That is why we have string memory here. And function modifiers, which is also another thing here that you see view. So it's the function definition is becoming very big now. Public, we understand. Returns, what it returns, we understand. What is this view here? The above function doesn't actually change the state in Solidity. You might write a bunch of functions that don't really change the state. What does changing the state mean? Changing any of these variables, either pushing to the zombies array, let's say changing DNA digits. We won't do that, but just for an example. In this case, you would declare it as view. If you know your function is not changing the state, you would declare it as view. Solidity also contains pure function. What is a pure function? Which means you're not even accessing the data. Here, there was a greetings variable. You were accessing it here, which is why this is view. It doesn't really change anything on the blockchain. So you can say that the modifier of this function is view. It doesn't modify the function. And what is pure? If you're not even reading the state, which is a very simple function like multiply, which takes two arguments and multiplies them, then you can say this function is pure. So what do we understand? Three things. One, if your function returns something specified here. Secondly, function modifiers, which can be either view or private, or pure. View means you're not reading anything. Pure means neither are you reading. This means not writing. This means neither reading, not writing. It's like a very sort of auxiliary function, takes two arguments and returns something from it. Cool. Put it to the test. Create a private function called _create random DNA. Very nice. Function _generate random DNA. It will take one argument, a string memory _str, and returns a uint. This was the syntax, right? Yeah, returns a uint. It is a private function, so we need to write private here. Don't forget to set the data location of _str to memory. We have already done it. This function will view some of our contracts variables. It won't change them, which means we can also set this to view. The function body should be empty at this point. We will fit in later on. Hopefully this is good enough and I'm not missing anything. Yep, looks good. Kekada 256. So this is a function that we will introduce now. I will just call it, I don't know how to pronounce it, so I'll just call it 256 or K256, and typecasting. So we're going to introduce two things now. What do we need to do at this point? We have written a function called _generate random DNA. We now have to write the function body. So we need to understand how you can create random numbers in Solidity. What's the way to do it in JavaScript? It's simply math.random using the math library. Unfortunately, Solidity isn't that easy. They don't make our lives very easy. They ask us to use a random library that gives us a random hexadecimal string that we then convert to a number, which is where typecasting comes into the picture, and then we do a modulus with this thing right here. So it isn't, how would you create a 10 to the power 16 digit in JavaScript that's random? You would simply do this, where this has like 16 digits. How would you do it in Solidity? You would pluck your hair out and then understand, okay, this is how you have to do it in Solidity. Let's understand how you do it in Solidity. Firstly, you call this, the K256 function on abi.encode packed of this. Now, what is this? Ignore it for now. We will come to it in probably the second or the third video. Let's copy this whole thing. Let's paste it here. What it says is, if you call this, it gives you a random string. We don't want a random string. We want a random number. What you can do is you can typecast a string to a number. Typecasting. It says, this is how you define a number. This is how you can, let's say the numbers you're defining are uint8 and uint. What is the difference? This is an 8-bit number. This is a 32-bit number, I think, by default. If you multiply them, it will throw an error because a into b returns a uint and not a uint8. But what you can simply do is, we can typecast b to uint8, and if you multiply a uint8 by a uint8, you get back a uint8. So what have we learned? This important thing. You can call some type and then pass in an argument, and it will convert this thing into this type of an argument. If you pass in a 32-bit number here and you call it with the uint, which is called typecasting, exists in other languages as well, it converts this b into a uint number, and then you can simply multiply it. Things are good to go. It says in the above function, uint, okay, you guys get the idea. Let's put it to the test. First line of the code should take the hash of abi.encode packed _ str. So this function takes an str input. The output that abi.encoded packed generates actually depends on this str. What this str is, we will come to in your application. It will be most probably the user ID or the name of the user if you're creating a Web2 app, because you want a random number generated for every user. Cool. We call this function, we got a random string right now. String that looks something like this. We still need to convert it into a number. To generate a pseudo random hexadecimal string and typecast it as uint. What they simply say is typecast it to a number, and you can do it. This string will get converted into a uint if you typecast this randomly generated string to a number. That's exactly what we have done, and store it in a uint called rand. So what have we done? We have generated a random number. How does the randomness get created, or what is the randomness? It's based on the _str string. If we call this function twice with the same string, we will get back the same number. Cool. Finally, we want DNA modulus to be only 16 digits long. So the second line of the code should return the above value modulo 10 to the power 16, which we've already luckily stored here in DNA modulus. All right, semicolon, semicolon. This is the code that we've written. First line gets a random digit in Solidity. This is the way to get a random long number in Solidity. You can also memorize it for now. This is the way. What have we done is we just typecasted a string, and you can do it in Solidity. And what is the string? It's a randomly generated string. How? Using this function. What this function does internally, we can come to at some point, not right now. Randomly generated number modulo DNA modulus will return a string that is 16 digits because we're moduloing it with 10 to the power 16. This is basic maths. If I click on check answer, it does work. Perfect. So until this point, we have a private function called _generate random DNA, and we have another private function which pushes to the zombie. We have not yet created the function that lets the end user interact with our contract just yet. That's exactly what we do here. Create a public function, create random zombie. It will take one argument, name, which is again its name, so memory. Public, because this is the one your end users will call. First line should be able to run _generate random DNA and pass in the name and store it in a uint variable called rand DNA. That's a little sus name, but okay. The second line should run the _create zombie function. Simple, straightforward. Pass in the name, and what is the other argument it takes? The DNA, which is rand DNA. This is very sus. Fourth line should simply be a closing brace. Okay, sounds good. So what have we done? We have created a public function. What does that mean? Once this contract is deployed on the Ethereum blockchain, anyone can interact with it. Anyone can call this function. Anyone can send in their name, which in the real world would probably be a user ID. You generate a random DNA for them, and you call the _create zombie function, which pushes it to this global zombie variables of yours, which means it's going to get stored on chain forever. Compare this to a Web2 website. In a Web2 website, this is the API endpoint that your user hits. They send in their name, maybe a cookie from which you get the name or the user ID. Then you generate in memory a random number, and then you store it in the database. So in a Web2 world, you would store it in a MySQL, MongoDB database. In the Web3 world, you simply store it here in the contract and it stays on the blockchain forever. How is a completely different story. This video is about how you create contracts and understand Solidity. Let's try to go through the whole contract top to bottom. Defined two variables. We want 16-digit numbers. If there is in the future a new contract called cat factory, and let's say cats only have 4 traits, then you could make this 8. Cool. DNA modulus, which is 10 to the power DNA digits. Why? It's needed later on when we want to modulo and get the random DNA, which is less than equal to 16 digits. We created a struct. We created a array of this struct type, which is initially empty. We defined a private function that pushes to the zombie given a name and a DNA. We defined a private function that lets you generate a random number given a name. Finally, we created a public function which first uses the first private function to get back a random DNA, then uses the second private function to simply push to this zombies variable. That's your basics of a very basic Solidity contract. Let's click on next. Last thing for this module is events. What are events? Very, very important, specifically important for our final app as well. Events are something your contract can emit. Why is this cool? Because after I've deployed my contract, for example, the final contract that we'll create, after I've deployed it somewhere, I will have a Web2 worker running somewhere. What is a Web2 worker? Basically something running on my AWS machine that will be watching this event, this contract, so that whenever someone actually pays 0.001 ETH or whatever, that centralized server picks up this event and then creates my Google Meet schedule or whatever. So if I had to discuss this on the iPad, in the real world, you don't want whenever events happen on the blockchain, you want to be able to emit them. If this is the highly complex blockchain and there is, let's say, a smart contract deployed here, you can have a Web2 worker. What is a Web2 worker? A Node.js process, a Golang process that says, bro, any event that this specific smart contract is emitting, please let me know. Why is this important? In our case, whenever you come and give 0.01 ETH, let's say a few of you do, and I become very rich, then you send 0.01 ETH here, and I have a Web2 worker running on, let's say AWS, which is listening to events here. Whenever the function exits and receives the 0.01 ETH, it will trigger an event here or trigger a callback here, let's say, which will actually create the Google Meet call between you and me. Hopefully that was clear. Let's see how you can emit events from a function or from a contract. Our contract is almost finished. Let's add an event. Events are a way for your contract to communicate that something has happened to your app's front end, which can be listening for certain events and take action based on what happened. Cool. You might ask, Kirat, what if the centralized logic is, never mind, that's too much for now. Come back. Events, how do we emit them? Example, this is how you declare an event. Okay, so your contract could have multiple types of event. One such type, for example, is integer added. If you have an add function which adds 2 things, it can emit a integer added event. Why is this cool? Someone might have called this and might have gotten this result, but someone else might be listening to events on this specific contract and be like, okay, addition happened for these 2 things and this was the final value that came. So how do you define an event? The name of the event or the type of the event, and then the arguments that it emits, which could be more than one. Your app frontend, for example, if you write JavaScript code or Node.js code, let's say, you could simply do your contract.integers added and then a callback function. So this code will get triggered again and again anytime this event gets emitted, which means anytime the add function is called. Putting it to the test. Unless you write code, you won't learn anything. Declare an event called new zombie, which you guys now probably understand. This event will be emitted when a new zombie is created. It should pass a zombie ID, which is a uint, a string memory name, and a uint DNA. Semicolon. Yep. Modify the create zombie function to fire this. Okay, let's look at the create zombie function. Fire it here. How do you fire an event? You simply do emit space the name of the event, which in our case is what? New zombie. And what are the arguments we need to emit? The zombie ID. What is the zombie ID here, Kirat? What could be the zombie ID? We'll come to it. It'll give us a hint. But before it does, nothing before it does. We need to understand what the zombie ID is. How do you give each zombie a unique ID? Well, you know that you're pushing to a zombies array. And the first thing that goes in there, you could just give it an ID 1. Similarly, the second zombie that goes in there, you could give it an ID 2, so on and so forth. So it says you're going to need the zombies ID. Array.push returns a uint. So whenever you do zombies.push, you can actually get back a uint, which it says you should store in ID and then simply use it in the event. So what does it emit? The ID, the name, and the DNA. All right. Now this is the time where I'm not very confident. I've written things very quickly. Let's quickly inspect what all we added. We added a new event. How do you write an event? Event name, event, the name of the event, and then the arguments, which in our case, uint zombie ID, string name, and uint DNA. Perfect. What is the second thing we did? We emitted the new zombie event in the create zombie function. So whenever this gets called, again, this gets called transitively, but whenever it gets called, this will be emitted. Question is, where do you get the ID from? You get it from zombies.push. This returns you a number. For the first one, it will either return 0 or 1. Second one, it will return 1 or 2, so on and so forth. And then you simply do ID, name, DNA. That's what it asks us to do. It says you're going to need the zombies array.push return the uint, which is the length of the array. So it will return 1. And since the first element in the array has an index 0, array.push -1 will be the index of the zombie we just added. All right. So one more thing it says is you don't want to store the first zombie that goes in should have an ID of 0 and not 1. This thing returns you the length of the zombies array once it's filled. So for the first one, it will return you 1, but we want the ID for the first zombie to be 0, which is why I added a -1 here. Okay. And finally, we emit the new zombie event. The syntax looks right. Emit, name of the event, and then the arguments. Perfectly. Sounds good. Should we do it? We have almost a perfect record until now. I'm not very confident on this one. There is an error. Most probably it's this memory thing. Maybe you don't need to specify string memory here. Do they have a string in their example? They don't. Okay, let's try again. That worked. Okay, so when you're creating the event, you don't need to specify whether it's of the memory type or the storage type. I think by default, yeah, there's no real, you're not really changing anything. So hence, I guess it doesn't matter. Cool. Moving on. I think we're done. First module is done, sir. It tells you you can write Web3 JS code to interact with this contract. So we've written the contract. This is what the contract looks like. This is what the contract looks like minus the events. Again, this sort of is a very weird UX. If you go back, it sort of takes away your changes, which is hard. But this is the contract more or less from top to bottom. Declare the functions, also declare an event here, which we just did. It went away. Declare the struct, create an empty array, create the zombies array, the private underscore create zombie function, which does emit an event. The underscore generate random DNA function that gives you a random number given a string, and finally the create zombie random zombie function, which your end users can call. How? That's what we see in the next slide here. It says if you want to write a website where you want to call this contract after you've deployed it on Ethereum, you can simply do something like this. It looks something like this. You can have a button. When the user clicks on the button, this is like jQuery code, you can get the name from the input field and then simply call zombie factory.create random zombie and send the name in. We will eventually see this in our contract. But if you understand a little bit of jQuery, you can see we could have a website which has an input box and a button. When the user clicks on the button, we call this function zombie factory.new zombie. Factory zombie.create zombie, and we pass in the name. So this is the logic that actually calls the function. Once the function is called, you can see we are also listening to the new zombie event here. And whenever the new zombie event gets triggered, again, this is JavaScript code that runs on the front end. If you don't understand it, it's fine. We call the generate zombie function, which will, let's say, on your website actually render the zombie based on the zombie ID by taking the first 2 digits, calculating the hat, taking the next 2 digits, calculating the eyes, so on and so forth. So if you want to, at this point, you can deploy the contract. You can write some front end code, and then you can look at the generate zombie sort of function, which actually gets the details of the zombie and returns them, which has the head choice, the eye choice, so on and so forth. And then you can finally render the zombie here. Cool. Module 1 done. Moving on to module 2. Proceed to next lesson. What is the next lesson? Zombies attack their victims. What do we have to understand in this? Let me go back to the slides. What we'll be understanding here would be cross contract calls, something called addresses and how you can use them, the require statement, inheritance, how you can import one contract in another contract, storage versus memory, which I guess we already discussed with a little bit more detail, function visibility, which I guess we've already discussed, but like some extra parameters other than public private, and calling other contracts, how one contract can call another contract. Let's get right into it. Alright, moving to the second section with a slightly cheaper webcam here because my DSLR battery died. We are going to learn about a few things in this second module. So would urge you to open the second lesson now. And this lesson says in the lesson 1, we created the function that takes a name, uses it to generate a random ID and stores it in the blockchain. In lesson 2, we're going to create our app more game-like. Until now, people can only create a zombie. Now let's add some gaming features to it. We're going to make it multiplayer and we're also going to add more fun ways to create zombies instead of randomly generating them. How will we create new zombies? By having our zombies feed on other life forms. So this might again feel a little weird. What are we doing here? We are just understanding Solidity. Unfortunately, the contract we're writing right now might not feel very day-to-day useful unless you're a game developer, but the whole idea is for us to understand syntax and just breathe through the contract for now. What does this one do, or what will it let us do? It will let us create zombies by having our existing zombie feed on another life form, which could be cat, a dog, something like that. Cool. Bear with me for some time if you don't understand that, or that feels weird. Feels weird to me as well. Frankly, zombies generally feel weird. Cool. When a zombie feeds, it infects the host with a virus. Oh god. I don't love this story, but okay. Let's see what it says after this. The virus then turns the host into a new zombie that joins your army. Okay. The new zombie DNA will be calculated from the previous zombie DNA and the host DNA. Okay. That seems slightly better. When you combine with another thing, for example, a cat, a new DNA is created, which is your original DNA plus some mathematical operation with the cat DNA, dog DNA, and something new is generated. Putting it to the test, you see the final UI on the right, which might feel like the final UI of your app. There is a simple demo of feeding on the right. Click on a human to see what happens when your zombie feeds it. So this is our zombie. These are humans. When your zombie feeds on that specific human, the no names DNA is this, which is the original zombie's DNA. The human DNA is this, and then the new mutant zombie DNA is this. So what have we done? Effectively, given a human, we have merged with them, mutated with them, bred with them, whatever you want to say. In the end, using your DNA and their DNA, something new was generated. A very biological concept. Might go over some people's head, which is fine. We just have to understand the solidity bits of it. Try another combination if you want to. If not, that's totally fine. This is what your game UI should finally look like. Even though the backend is on chain, your front end should look something like this. It should allow the user to merge with a human, a cat, whatever. We will see what that is. Cool. Let's get right into it. Mappings and addresses. So a new thing is introduced here. We understand structs, we understand arrays. Let's understand what are mappings and what are addresses. Let's make our game more multiplayer by giving the zombie in a database an owner. So every zombie in a database will have an owner. An owner usually is where you need to sort of digest a new concept. An owner is an address. What is an address? Think of it like a user ID in the real world. In the Ethereum world or general blockchain world, it's a public-private key pair. Again, you can go back to my Web3 roadmap, the original one, where I sort of explained this slightly better. But every user on the blockchain has a private key and a public key. Their public key is what's called address here. And what they're saying is, to make our game more multiplayer, we should give our zombies an owner, which would be an address. Cool. Now, what is an address? In Ethereum, the Ethereum blockchain is made up of accounts, which you can think of as bank accounts or user ID passwords on a Web2 website. An account has a balance of Ether. Just like you have a bank account where you have a net banking ID and a password and you have some INR in it, you can on the blockchain have an address which has some Ether in it. Where it comes from is a whole different story. Usually people get it from centralized exchanges like Binance or some other centralized exchange like Coinbase. And you can send and receive Ether payments to other accounts. So this is the general thesis of Bitcoin and Ethereum, right? You have ETH, you have BTC. Oh, sorry, this is the camera. You have ETH, you have BTC. You can just send it to another one. Each account has an address, which is like every user has an address. Address usually looks something like this, yada, 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 bunch of things. Feel free to pause and read through it if you'd like. The second thing it introduces is mappings, which is similar to maps in TypeScript, similar to maps in C++. So basically a mapping from address to uint or uint to string, like any type to any type, basically similar to an object in JavaScript or like a map in C++. It's like a key value pair. A mapping is essentially a key value store for storing your data and then looking it up. Perfect. If you've used maps in TypeScript, if you've used maps in C++, I think Java has them as well. The same thing. To store the zombie ownership, we're going to use two mappings. One that keeps track of the address that owns a zombie, and other that keeps track of how many zombies this owner has. So we have to introduce two maps here. The first one is going to keep track of who is the owner of a zombie. So what will the map be called? Zombie to owner. The key will be a uint, which will look up the zombie based on the ID. So it will be the zombie ID, and the value will be an address. So if you want to ever get the owner of a zombie, you can come back to this. How do you define a mapping? This is how you define a mapping, and then we'll see how you can actually use the mapping and sort of put data in it and get data from it. Cool. First, it says just create a zombie to owner mapping. I'm going to declare it here. What is the syntax? Mapping space. What is the key? It's a uint, which is the ID of the zombie. And what is the value? It is an address. So this is also an identifier in or a string in Solidity, a type in Solidity, an address. It's basically a string for all practical purposes that looks something like this. It is like a public key or a public address of an Ethereum account. Cool. This is the first mapping. What is the other mapping it asks us to build, or what does it want us to name it? Zombie to owner. What is the other one? Starts from an address, ends to a uint. It's called owner zombie count. Basically will store how much zombie a single owner owns. Why? We'll come to later on. But at this point, can you think of where exactly should we call owner to zombie count of address plus plus? In which of these functions should we call this? I mean, we will come to it in the next module, but can you guess it already? Try to pause it and try to think of which function we should put it in. For now, this module just asks us to declare them, not use them. That is what we have done, and we'll check the answer, and it is wrong. Syntax, no, looks good. Variable names, no, looks good. What could be wrong here? Mapping uint to address, key will be uint, and the return value will be address. Oh, make it public. That is one thing we haven't done yet. Public. Create a mapping called this where the key is an address, value is uint. It did not ask us to make it public, so we won't. Perfect. Cool. We have defined two things at the top. One of them is public, one of them isn't. Let's move on. Now we will have our our mapping. Now we will have our mappings keep track of who owns the zombie and maybe also increase it. The question to ask is, how do you get the address of someone who has called a specific function? If someone calls this function, whenever a function is called, specifically a public function is called, whoever calls it will have an Ethereum public key. They will actually pay some gas to call this function, and they will have a public private key pair. They'll have an Ethereum account. You will actually deduct some ETH from their account, 0.0001 ETH, and only then will they be able to call this function. Question is, how do you get the address of the person who has called this specific function? And the answer is using message.sender. So message is a variable you have access to here. And if I just write message.sender, you get the address of the person who made this function call. Eventually, when this is deployed in the blockchain and someone actually calls it, to get the address of the person, simply get it using message.sender. Why do we need it? Because here it says, first let's update our underscore create zombie function, which is this guy right here, to assign ownership of the zombie. So here it says I have to assign ownership of this guy. First, after we get back the new zombie ID, which is this ID right here, let's update our zombie to owner for this ID is who? It is message.sender. Why message.sender? Where message.sender? Throughout the life cycle of this function being called, you can access message.sender and it will give you the person who called this function, which transitively called the underscore create zombie function. Cool. We have this mapping sorted. Second, let's increase the value of this for this specific user. So owner zombie count of message.sender plus plus. So we have now populated the two mappings that we had defined, where in the underscore create zombie function. You might ask, Kirat, can I not do it here? I will say yes, you can do it here. It's the same thing. Doesn't really matter. In Solidity, you can increase my plus plus. That's exactly what we have done here. Hopefully that is good enough. That is good enough. Cool. Moving on. Require, a new thing that is introduced. You all needed to know, you can sort of get away without using require as well, but it's a nice sort of exception thrower when you know something should happen and isn't happening. What does that mean? Let's understand. Let's just put it to the test. In our zombie game, we don't want users to be able to create unlimited zombies. Makes sense. You want to somehow rate limit them by repeatedly calling this public function. Now this function is public, but you don't want people to keep calling it again and again and create 10,000 zombies. So it says put a require at the top that says, puts a check to make sure owner to zombies of message.sender is equal to 0. And if not, throw an error. So this is similar to being something like, if the count is 0, then do this. Oopsie daisy. Then do this, else throw some error. You can either write this big if else, or you can at the very top of the function simply be like, require that this guy has no zombies just yet, and only then will the function proceed, else there will be an error thrown here. Cool. Why is this good? Because now we know any address on the blockchain can only create just one zombie, not more than one. Check answer. Good to go. Moving on. Inheritance concept comes from Java, object-oriented programming. What does it say? Our game code is quite long, and I don't disagree, which means I agree. It is a very long sort of one big contract, and you don't want that. You want to break your contract into subcontracts, and this is very common across languages. You use extends, implements in Java, and they just let you do a bunch of things. Inheritance has some other properties and uses, but one other thing they let you do is break your contract into small subcontracts. So here it gives a good example. There is a contract called Doge, which has a function, and then another contract called Doge, which is, baby Doge, which is Doge, which means it extends it, which basically means you can access this function there and also access this function. Cool. Baby Doge inherits Doge, which means that if you compile and deploy Baby Doge, you will have access to both catchphrase, which is this guy right here. You will also have access to the other guy. Cool. Put it to the test. In the next chapter, we're going to be implementing the functionality for our zombies feeding and multiplying, the dumb thing that they want us to do. Let's put this logic in its own contract that inherits its method from the zombie factory. So they're saying this zombie factory looks pretty clean. Lets you create a new zombie, and also we've now added rate limiting here. Now let's create a fetch contract that extends this original contract so that we write all the mutation logic there. What's the way to write a contract? Contract, name of the contract, which is zombie feeding, and it should extend zombie factory. This is good enough. That's all it asks us to do just yet. If you deploy this contract, it will have all the functions that this contract has as well, all the variables. So you basically have access to everything. Right now, this contract is the same as this contract. There's no difference between them. Cool. Let's check answer. Good to go. Import. Now you can keep defining bunch of contracts one below the other in the same line, in the same file, or you can just import from one file to another. That's what they basically tell us here. Again, very common in various languages. The way to do it is import and the name of the file that you want to import from. When you do it, you have access to everything that's defined in the other file. So what have we done? We've just put the zombie factory in its own file, and the thing that we had defined here at the bottom, zombie feeding, we just moved to a new file and imported the other file here so that we have access to zombie factory. Cool. Fairly straightforward. Check answer. Good to go. Next chapter. Storage versus memory. We discussed this a little bit in the last section. Let's try to dive deeper into it. In Solidity, there are two locations where you can store variables. storage or in memory. Storage refers that the thing is permanently stored on the blockchain. Memory variables are temporary. If you create a function which has string memory, the string is just available for the life cycle of the function. It doesn't actually get stored on the blockchain. But if you use storage somewhere, that means you want to put this on the blockchain. So what does it say? Most of the times you don't need to use these keywords because Solidity handles them by default. State variables are by default storage. The variables that you've defined are declared outside the function, which means like these variables right here, these are storage and are permanently written to the blockchain, while variables declared inside the functions are memory and will disappear when the function ends. So anything that you define inside a function will disappear when the function goes away. It's not really stored on the blockchain permanently. However, there are times where you need to use these keywords, namely when dealing with structs and arrays within functions. Okay, so what does it say? There are cases in which you need to specify whether this is storage or this is memory, more especially when you're using structs and arrays. Let's see how. They say there is a sandwich factory. There is a struct. There is a bunch of sandwiches similar to our zombie factory. There is a eat sandwich function. Here we define a storage my sandwich. So what does it say? It says this thing, which is sandwich my sandwich equal to sandwiches of index, seems pretty straightforward, but Solidity will give you a warning telling you that you should explicitly declare this either as storage or as memory here. So instead, don't ever do this. Do this. You should declare it either as storage, and if you make a change here, it will be permanently stored on the blockchain. You can also declare it as memory. If you make a change here, it will simply be a copy of the data, which means you will modify this temporary variable. It won't actually change on the blockchain. Why is this useful? We will come to. But hopefully you understand, whenever you're dealing with a single object of an array, you can either define it or get it from sandwiches of index as a storage variable or a memory variable. If you get it as a storage variable and you change it, it is permanently changed on the blockchain. You don't have to put it back into the global sandwiches sort of array. It just permanently changes when you're defining the function, you've specified storage. If you've not, if you've specified memory, it's like good to go. This is a temporary variable defined here, goes out of memory here, and you don't change it on the blockchain forever. Cool. Putting it to the test. Create a function. Let's create a function. Call it feed and multiply. So this is where it might feel like why we're doing this, and this is just how they've designed the game. It takes two arguments, a uint called underscore zombie ID and a uint called underscore target DNA. Alrighty. This should be a public function. You don't want to let someone else feed on our zombie. Okay, I don't know. I don't even frankly understand what these lines mean, but let's see. So first, let's make sure we own this zombie. Okay, add a require that says that message.sender is equal to the owner of the zombie. How do you know if message.sender is the owner of the zombie? There is a mapping we generated in our original contract, the zombie to owner mapping. This takes a zombie ID as input and gives you the owner. So what are we doing here? We're checking this public function called feed and multiply. Whoever calls this function, this function could be a section on your website where a person clicks on a button. You take the zombie ID that they want to update as an input, and you want to make sure the person that's trying to update the zombie actually owns it. This might feel a little jarring. If it doesn't, feel free to skip through this section, but let me quickly explain this. You will finally have a website where people have, let's say, a create zombie button and then an input box where you can give a name to your zombie. When you click on this, a contract call happens and we store this in the zombies array. We also store the mapping of who the owner of this ID is. In the future, your user might go to a different page and there they would have an input box that says, give me the zombie ID you want to mutate, and then a button that says, whatever, do it. When they click on this button, the contract call that happens first needs to verify that this user that's making this call, the address of this user, is the actual person who owns this zombie ID. Only then should you allow them to run everything that we are going to write after it. You should not allow them to change this function, like call the function body actually mutate for someone else's zombie. I can only update my zombies, which is why a require statement at the very top. Beautiful. Add a semicolon here. Moving on. We are going to need to get this zombie's DNA. So the thing our function should do is declare a local zombie. All right. We are going to need to get the zombie. Okay. Called my zombie, which will be storage. Alrighty. Which is equal to zombies of underscore zombie ID. Let's set this variable equal to zombie ID in our zombie. Okay, sounds good. So basically this line right here. This was the third point. What was the second point? Require. What was the first point? Create a function. All right. You should now have 4 lines of code. I indeed have 4 lines of code, sir, including the closing breaks. I do agree, sir. I have 4 lines of code. Cool. So they say we'll be continue to fleshing out this function in the next part. For now, add a require statement and at least get the my zombie. Why storage? Because we will change the DNA of this thing, because this guy is mutating, basically trying to reproduce with this other targeted DNA. We'll come to what that is in the next part. For now, understand require, understand a storage variable. Why storage? Because we want to change this user's DNA. Moving on. Oh, sorry. Let's first check. Fucking A. Was that right? Hopefully that was right. I did not check. It looks right. Cool. Zombie DNA. Let's finish the feed and multiply function. The formula for calculating a new zombie DNA is simple. It's the average between the feeding DNA and the target DNA. Sounds good, fairly straightforward. Just plus divided by 2. Put it to the test. If we have required and we have ensured that this user actually owns this zombie, you just need to update this zombie's DNA. First, make sure that target DNA isn't longer than 16 digits. Okay, sounds good. To do this, we can set underscore target DNA equal to underscore target DNA modulo DNA modulus. You might ask, Kirat, where is this coming from? This contract does extend zombie factory, where we had defined DNA modulus to be 10 to the power 16. So if the user gives us a very big DNA, we just pad it down to 16 digits. Next, our function should declare a uint, okay, called new DNA, which is equal to average of my zombie's DNA, which is my zombie.dna, I think. Yep, my zombie.dna plus the target DNA divided by 2. If you take the average of two 16-digit numbers, it will also be a 16-digit number. All right, once you have the new DNA, let's call create zombie. Once you have the new DNA, let's call create zombie. They're not making us update the original zombie. They're asking us to create a new zombie. That sounds weird, but let's see. You can look at the zombie factory.sol. If you forgot which parameters to pass in, note that this requires a name. So let's set our new zombie name to this for now, which is no name. That's the first argument. And you can write a function to change the zombie's name later on. Alrighty. So they said, whenever someone says mutate or feed and multiply, given my zombie ID and someone else, we create a new zombie. We don't change the original zombie. My question at this point is, why did we use storage if we did not have to change my zombie? And hopefully we will come to this later on. But for now, I have done everything it asked me to do. I've called create zombie here, which if we go to zombie factory.sol is our original function that we wrote, which had the logic to push and then add a new zombie for this owner. That is exactly what we have done. So you might notice at this point, a single owner can now have 2 zombies, because our original public function create random zombie only lets them create it once, but our other function lets them create it twice. That's exactly what we've done here. Check answer. Good to go. Next chapter. Okay, let's do it. More on function visibility. Okay. Code in our previous lesson has a mistake. If you try compiling it, the compiler will throw an error. Interesting. The issue is that we tried calling underscore create zombie from within zombie feeding, but underscore create zombie is private. Beautiful. They said underscore create zombie, this function that we called, is a private function, which means it can only be called inside this contract. However, we called it here in the zombie feeding contract. How can you allow a function to be called by another function that extends it? Here we introduce internals and externals. In addition to public and private, there are two more types, internal and external. Internal is the same as private, except it also has is accessible to the contracts that inherit from it, which basically means this is what we have to do for create zombie, because this other contract that inherits from it needs to be able to call it. What is external? It is similar to public, except that these functions can only be called outside the contract. They cannot be called by other functions inside the contract. Weird. Okay, so seems like a use case where you might want a function to be only called outside the contract but not within the contract. For that you use external. And internal is the same as private, except that it's also accessible to the contracts that inherit from it. Cool. So you understand internal. Hopefully we understand external as well. Declaration is fairly simple. Just replace private or public with internal or external. Cool. Put it to the text. This needs to become internal now because our zombie feeding function needs to be able to use it, which is not in this same contract. It is another contract which inherits from it. So this is moderately private, cannot be accessed by the outside world, but can now be accessed by zombie feeding. Check answer. Good to go. What do zombies eat? This is where things get more weird from like the game logic. It is time to feed our zombies. And what do zombies like to eat most? Well, it just so happens that crypto zombies love to eat crypto kitties. All right. Yes, I'm serious with a happy emoji. I don't think you're serious, sir. But okay, I will play along. It says the thing that you need to eat, the target DNA, probably is of a cat or like a kitty more specifically. In order to do this, we need to read kitty DNA from CryptoKitties smart contract. We can do that because CryptoKitties data is stored openly on the blockchain. Isn't the blockchain cool? So let's take a step back. Let's first understand what CryptoKitties is. CryptoKitties is another smart contract. Okay, it's out there in the world, and they also have a similar concept of a DNA. Only the final thing that it spits out is not a zombie. It is a kitty or like a cat. Cool. Now it says the thing that you're mutating with is a cat. So the zombie mutates with the cat to create a new zombie. And the question really is, how do you interact with this other contract? Why do you have to interact with it? Let's see. For our contract to talk to another contract on the blockchain that we don't own, we first need to define an interface. Okay. Why do we have to interact with it? We will come to. How do you interact with another contract on the blockchain? You use something called interfaces. Let's look at a very simple example. Say there was a contract on the blockchain that looks something like this. All right. This is another contract that exists on the blockchain, not our contract. It's called lucky number. This would be a simple contract that where anyone could store their lucky number. Okay, let's look at it. There is a public function called setNum, and it says numbers of message.sender equal to this num. So anyone can call this public function. When they do, you set their value. There's also another public function using which you can get any person's lucky number that they've put on the blockchain. Very simple contract. This would be a simple contract where anyone could store lucky numbers and it will be associated with their Ethereum address. That's exactly what's happening on this line, because people can call this public function, pass in a number when they call it. You can give arguments when you're calling a function on the blockchain, and we simply set numbers of message.sender to this number. So I can be like, my lucky number is 7. I will call this contract from my Ethereum address with the number 7, so on and so forth. Now let's say we had an external contract that wanted to read data. So there's another function called getNum that lets you read data. Let's say we want to read this from one contract, not from my browser, not from someplace else, from one contract. One contract needs to read the code of another contract. How do you do it? For that, they say we first have to create an interface called contract number interface. And these are similar to interfaces in Java. Basically gives you the signature of the function that exists in this contract without the function body. What does it give you? Whenever you create an interface, you write, okay, contract name of some random name of the contract you want to give it. You write the signature of all functions, which means not the body, but everything else. Function, name of the function, the argument it accepts, and public view returns you and everything. And you define this in an interface. Notice that this looks like defining a contract with a few differences. It's almost a contract, but for now, we're only declaring the functions we want to interact with, which is getNum. We don't have to put the other function here. Secondly, we're not defining the function bodies, only the signature. So it's kind of like a contract skeleton. It is the skeleton of this other contract. And why is this useful? Let's go down. This is useful because whenever you want to call a function from one contract to another, you need to sort of tell Solidity this is what the other contract looks like, because other contract is some bytecode somewhere. You can't simply be like other contract.random function without actually telling Solidity what the function looks like, at least what is the function signature. Which is why whenever you want to do smart contract calls from one smart contract to another, which is not from my browser, one contract needs to call another contract. You need to define the structure of the functions in the other contract that you want to call. So smart contracts can call other smart contracts, but when you want to do that, you want to describe the structure of it. Now it says the CryptoKitties source code, which is like, actually, believe it or not, a real contract that exists out there, which is like a CryptoKitties contract, which lets you do something similar. Lets you create kitties and give them DNAs. It looks something like this. This is the function body, and this is the sort of get kitty function that lets you get a certain kitty given an ID, and this is what it returns. A bunch of things it returns. The function looks a little different than what we're used to. You can see it returns a bunch of values, not just one. So you can actually do that. If you're coming from a programming language like JavaScript, this is in Solidity, you can return more than one thing. A single function can return 2, 3, 4, 5, how many values. Now that we know what this function looks like, we can use it to create an interface. So this is one of many functions that exists in a different contract called the CryptoKitties contract. We want to make a function call from our feed and multiply function to that contract. So what we do, first we define an interface, because only after we can define an interface can we make the function call. Cool. Define an interface called kitty interface. Okay, what's the syntax to define an interface? Fairly straightforward. It's contract, name of the interface, and then the function signature, which they have luckily given us the function signature for CryptoKitties. Remember that it looks just like creating a new contract. Inside the interface, define the get kitty function. So function get kitty, which should be a copy paste of the function above. Okay. If you look at this get kitty function, it is return external view and returns this thing. Again, we only need the signature. We don't need the actual function body when we're defining the interface. And that's exactly what we did here. All right. So what have we done in this specific section? We have just created an interface, not a contract, an interface. It is almost a contract, only it gives you function signatures, not an actual function. Why is it useful? It is useful if you want to interact from one contract to another. I also need to put a semicolon here. This is the only code that we have added in this section, which is creating an interface to another external contract, which is a very complicated contract. We don't need to worry about what it looks like. We just need to worry about one such function that it has, which is the get kitty function. Why? Because that's what we're going to feed and multiply with, a kitty. I know it's weird, but like, let's deal with it. Feel free to pause here. I'm going to check and answer, and victory. Cool. Using an interface, defining an interface is straightforward. How do you actually make a contract call to, which in this case is like get kitty, to get back some kitty details given an ID of a kitty? You can use the contract as follows. First thing you have to do in your original contract is define where this kitty contract is stored. So whenever we haven't yet deployed a contract, we're just writing Solidity code and checking answer, compiling it. We haven't yet put it on the blockchain. Whenever you put a contract on the blockchain, you get back a contract address, which looks very similar to a public private key pair for your own Ethereum account, right? So what it says is, whenever you want to use an interface in your own contract, you at the very top have to define the address of the other contract that you want to call, which in our case is the kitty interface contract. Cool. Once you've done that, you can simply be like name of the interface, some variable name that you want to give, equal to name of the interface, and then the address of that specific contract. Effectively, this is like telling the shape of the contract, which is the number interface, and telling where this is stored on the blockchain. So you can think of it like a backend server in the Web2 world, which is giving you the types also. Okay, this is the type of post calls that you can make, get calls that you can make. That is what we've stored here. And this is the, let's say, URL of the backend server. Similarly, address of the contract where it's stored on the blockchain, and the interface, which defines what are the functions that you can call on it. Again, this could have multiple functions. Our interface only needs to define the ones that we need to use, which in our case is the get kitty function. Finally, to call this function, you can simply be like uint num equal to number contract dot get num. What is number contract? The thing that you have defined here. Cool. Let's try to call the get kitty function from the kitty interface. For that, we need the address of the CryptoKitty contract, which already is here. If you copy it and go to Etherscan, you can probably see a smart contract here, which is the CryptoKitties smart contract. As you can see, it says CryptoKitties. Okay, so there is an address there. This actually has a smart contract, and if you look at the smart contract, you will see a get kitty function. So there is actually a Solidity smart contract out there which exists on this address. It is currently residing on the Ethereum blockchain, and it has this get kitty function. We just got the signature of the get kitty function and we put it here in our interface. And what's the next thing we did? We first have to initialize the kitty contract. So how do we do it? Address kitty, variable name called ck address. I've saved the address, ck address. Oh, they've already saved it. In the next line, create a kitty interface. Okay, let's create a kitty interface. What do we call it? Kitty contract. Initialize it with kitty interface of ck address. All right, this syntax looks right to me. Yep, looks right. We have access to this kitty contract variable now, and then later on we will see how we can call the get kitty function. But for now, we at least have access to the kitty contract variable. I've saved this. Just okay, cool. Just have the variable for now. We'll see how we actually do the function call. Next, handling multiple return values. Get kitty function, as you can see, returns multiple things, not just one. You can do that in Solidity. You can actually do that in multiple languages. Even in JavaScript, you can return like a tuple or like an array of 2-3 values. Similarly, in Solidity, you can return multiple things here. Okay, for example, 1, 2, 3. And if you want to get these values on the left hand side, you can simply be like a, b, c equal to whatever this guy returns. So if it returns 1, 2, 3, the value of a will be 1, b will be 2, so on and so forth. Hopefully fairly straightforward. If you have more than one thing here that the function returns, you can get each one of these into variables. How? Like this. Cool. What does it want us to do? It says make a function called to feed. Make a function called feed on kitty. Okay, let's create a function called feed on kitty. It will take two uint parameters, underscore zombie ID, which is a uint, and underscore kitty ID, which is also a uint. Should be a public function. Okay, sir. The function should first declare a uint name kittydna. Okay. Note, in our kitty interface, genes is a uint 256. If we look at genes here, it is uint 256 indeed. But if you remember back in the lesson 1, uint is an alias for uint 256. They're the same things. Oh, I thought it's uint 32. Apparently not. Uint in Solidity is actually uint 256. Sounds good, sir. So they're basically the same thing. The function should then call kitty contract dot get kitty. All right, let's do that with the underscore kitty ID. Alrighty, sounds good. And store the gene in kittydna. It returns a bunch of things to us. As you can see, it returns 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. We just need the genes. How can we get it? You can either declare 10 variables here and then be like v1, v2, v3, dot, 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 and then finally kittydna equal to this, similar to how they let us like described how you can do abc equal to some function name, or they gave us a very nice hint here. They said if you don't need the values before, you can simply add commas. So what do I need to add? I need to add maybe 9 commas. 1, 2, 3, 4, 5, 6, 7, 8, 9, either 9 or 10, but 10 to be exact. Remember, get returns tons of variables, 10. So the first variable will be here, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th variable is kittydna. Looks good. Be careful. The last one is genes. Sounds good. Finally, the function should call feed and multiply. So this is the public function that people will call now. You will get the kittydna from the kitty ID, and then finally you will call feed and multiply with the zombie ID and the kitty DNA. So how is this feed on kitty function different from feed and multiply? Feed and multiply just takes 2 DNAs, takes the average, creates a new zombie. Feed on kitty is for you to feed on an actual kitty. It's like a crypto kitty that exists on the blockchain in this smart contract. You just have to give the ID of the kitty, which is similar to the ID of our zombie, which starts from 0, 1, 2, 3, 4, 5. Similarly, kitty's ID starts from 0, 1, 2, 3, 4, 5. You might have heard of like bored apes, which start from 1, go up to 10,000, a bunch of NFTs that exist. Think of this as a very similar thing where each one of them has an ID starting from 0, going to, let's say, 999. You just give the ID of the kitty. This function gets the DNA of the kitty. However, if you go through this whole contract, you will see how a kitty is actually generated, like how the DNA of the gene of the kitty is generated. We just get the DNA for this specific kitty and then call feed and multiply, which doesn't care about whether the target DNA is of a kitty, of a person, of a dog. This function is a more generic function, which given two DNAs creates a new zombie. This function is specifically for kitties. If you know you want to multiply or feed with a kitty, you call this function. In the future, if you want to feed with a dog, you define a new function here and then you feed with another dog contract that might exist. If you want to feed with a bored ape, let's say. So what is the use case here? Use case is someone sees bored ape is a very famous sort of NFT collection, and they want to create their own NFT collection, which lets the users mutate with bored apes. What will be the final outcome? An ape with like some funny thing. If you don't understand this, don't worry about it. Like just thinking of a use case here because I don't see any. Feed on kitty is a function, public function we have defined, takes two inputs, your own zombie ID. Why do I say your own zombie ID? Because if you don't send your own zombie ID, we have this require here, it will fail. If you send a zombie that you do own and you send a kitty ID which does exist on CryptoKitties, you can actually mutate them and create a new zombie out in the world using this function right here. That is a quick summarization of what all we have done until now. The important thing to learn from this is one smart contract can actually call another smart contract, and this is the way to do it. You define the interface of the other contract in the kitty interface variable. Specifically, this could have contract has a bunch of functions. We only care about this function, and that's what we defined here. Finally, you give the actual on-chain contract to this variable. You initialize the contract, not the interface now, the actual contract, and then you can call functions here. For example, kitty contract dot get kitty. Cool. If you want to call another function, you will have to define it in your interface, else it won't work. What are these functions? There are a bunch of these that exist here. You can actually go through this contract. It has very nice comments and you can figure out what exactly CryptoKitties does. But we don't have to worry about that just yet. Think this should work. Let's move. Oh, oopsie daisy. Hopefully that was right. I did not check. I forgot to check. Bonus kitty genes. Our function logic is now complete, but let's add a bonus feature. Let's make it so that zombies made from kitties have some unique features, so that you know that there are cat zombies. All right. To do this, we can add some special kitty code in the zombie DNA. Sounds good. What they're saying is, whenever you call feed on kitty and a new zombie is created, you want to make the DNA slightly special. Maybe add 1 0 at the very end, or I don't know, add 3 zeros in the beginning, so that you know this is a cat zombie, not like a normal zombie. So your UI can basically show some sort of cat with the zombie. Cool. To do this, we can add some special kitty code to the zombie's DNA. If you recall from lesson 1, we're currently only using the first 12 digits of our 16-digit DNA. So there was a 16-digit DNA, but there are only 6 sort of characters of our zombie, like a hat, eyes, mouth, so on and so forth. We actually have access to 4 digits. What it says is, what we'll say that the cat zombies will have 99 as the last 2 digits. Cool. If there is ever a zombie that is created which has 99 at the very end, then that is a cat zombie. How do we enforce this? Let's see what it says. It says if statements, and this is where they introduce sort of if statements. You need to put an if check somewhere, and this is how you make an if check. We already knew this, fairly simple stuff. Question is, how do you make sure anyone who calls that function, the final DNA that is created somehow has 299 at the very end, because that is how our front end will identify if this is a cat zombie or not. Let's see what they say. First, let's change the function definition for feed and multiply. So it takes a third argument, a string named species, which we will store in memory. All right, let's go to feed and multiply. This function right here, it takes a third argument. Again, as I said, this takes 2 arguments right now. Doesn't care if it's a cat or a dog, whatever. But now we are making it char. We are saying the third argument needs to be a memory string, which is called species. Next, after we calculate the new DNA, which is target DNA right here, or new DNA right here, if we let's add an if statement which compares the K256 hash of species and the string kitty. We can't directly pass strings to this. Instead, we will pass abi.encoded packed string as a argument to the left side and abi.encoded packed kitty as an argument to the right side. Yeesh. Okay, let's read through this again. It says next, after we calculate the DNA, which is this guy right here, let's add an if statement comparing the K256 hashes of species and the string kitty. So compare K256 hash, which is this guy right here, of the species and the string kitty. All right. Let's see where we're building up to with this. They actually give us some hint here. Let's read through it. Eat BLT. Remember, with strings, we'll have to compare their K26 hashes to check equality. So whenever you're comparing strings in Solidity, you can't simply be like A equal to B. You have to compare their K256 hashes. That is exactly what we are doing here. So we're checking if the third argument was kitty. All right. If the statement, we want to replace the last two digits with 99. If this is true, which means a kitty was indeed passed, we want to change the DNA to have 99 at the very end. How will we do it? They give us a very nice mathematical function for it, which says new DNA equal to new DNA minus new DNA modulo 100, which means it will remove the last two digits. These are the last two digits. You remove it from new DNA, so the last two digits become 00, and then you simply add 99 to it. So this function will add 99, like remove the two digits and then add 99 to the end. So the new DNA will for sure have, doesn't matter what the first 14 digits looks like, the last two digits will definitely be 99. Lastly, we need to change the function call inside feed on kitty and then pass kitty as the argument. Why is this cool? This is cool because you could in the future add dogs and then add another if check here that if it is of the type dog, you add 98 to the very end, and so on and so forth. So this sort of lets you define the type of mutation that you've created. You can create multiple sort of these reproductions with a kitty, with a dog, with a person, whatever. And then when you do the DNA sort of digits, you can just look at it and tell, okay, this was a zombie with a cat, zombie with a dog, so on and so forth. One sort of bug I see here is, what if the original zombie that you're creating here, and they're creating like a random DNA, what if it has 99 at the very end? It could, right? If it has 99 at the very end, then you're screwed. You probably should make sure that it is not 99 at the very end, else people will create a random DNA which has 99 at the very end, and your front end would feel this is a cat zombie even though it isn't. Cool, makes sense. Hopefully it makes sense. You should make sure that 99 comes to the very end only if it is a mutated zombie and not an original zombie. Cool. Alrighty. I think this is good enough. Check answer works. Moving on. I think we're done. What have we learned? Given a very famous NFT collection out there called Crypto Kitties, and given your dumb zombie collection that no one uses, you can mooch off of them by allowing your users to mutate or reproduce with them. Once they do, a new zombie is created, which is the combination of their DNA and your own DNA, actually modulo 2. But the important thing for these cat zombies is it has 99 at the very end. So what you can do is, whenever a DNA has 99 at the very end, you can add a tail to the zombie, which would tell your end users, yeah, this is a cat zombie. Cool. JavaScript implementation. I think somewhere here they might actually do some logic to add a tail or something. I don't know. You can read through it. Notice that these cute cat legs on your new zombies. Do you notice the cute cat legs on your new zombie? That's our final 99 digits of DNA at work. All right. Have we used it somewhere here? So they use this API to get a specific CryptoKitty. All right, I get back a CryptoKitty. I actually have an image for it. This is what CryptoKitty 1 looks like. Okay, it looks something like this. If I mutate with it, I should hopefully see the legs from this kitty. So that's what they're trying to probably do here in the front end. Let image realize this. Do something display with the image. Yeah. So you can write front end logic so that given a CryptoKitty that you're mutating with, the legs that your final zombie gets is a combination of your legs and like the kitty's legs or like your whole body. Cool. Again, weird use case. Don't worry about if you don't understand it. Hopefully you understand creating contracts, inheriting contracts, calling other contracts, importing from one contract file to another contract file. That's the important bit. We'll get to more realistic use cases very soon. Moving on to the third part. All right. Hi everyone. So by this time you've completed the first part. So congratulations. Today is 10th of August.
Yep.
Which is the day that this video is being released. It was supposed to be released today, but the second it just came out, and the second part, the part that you were supposed to look at, sounds something like this. So there's basically two audios, one from this mic, one from laptop. That's my fault. So we have to reshoot it. Just wanted to give you a behind the scenes sneak peek into being a YouTuber. Okay, at 12:28 and my head is pounding really bad. But we committed the video today, so we have to release it. So I'll be shooting it now. Hope you guys like it, and please stick through the end of it. Now I feel there's a lot of effort gone into this one. Alright, thank you. See you in the video. Alright, after a few mic checks, we're back at it again. This is part 3, where we're going to understand two important things. One, gas optimizations, how you can optimize your contract code a little bit so that the end user doesn't pay a lot of gas. What is gas? And secondly, how there are a bunch of use cases that come when you're writing a contract, and then there's an open source library called OpenZeplin that has written very nice contracts that you can simply copy paste and bring into your own contract. The benefit here is that these are very well audited, they're very well written, they do what they're supposed to do, and then you can also verify that the Solidity contract does something it says, and you can simply copy paste them and use them in your contract. That way you don't have to write all of that logic yourself. Cool, let's get right into it. So the first part, in you now have to go to Crypto Zombies, and then the third section right here, I would urge you to do it yourself. Here it says, congratulations, I'd already done that. So we're at the very end. Let's go to the very beginning. It says immutability of contracts. What this means is contracts on the Ethereum blockchain are immutable. Once you've deployed a contract, it will stay there forever. You cannot change it. This is why there's a lot of backlash to ETH that, oh, money gets like stuck in contracts forever. You can't change it. Yeah, that's by design. ETH was meant to be, if you want to put your money somewhere, if you're sending ETH somewhere, you want to make sure the contract cannot be changed in the future, which is why immutability is a construct and probably a good construct for ETH. Now, this has a bunch of downsides. One such downside they will share here, but generally the downside is if there is a bug in your contract and you deploy the contract, it is there forever. And let's say people interact with it, people put money into it. What is putting money into it will come to the next part. But let's say people interact with it and then you realize there's a bug. You can't change the code there. Unlike traditional Web 2 systems where you can just push code to GitHub, pull it on your server and you're good to go. Cool. What can be an attack vector here in the zombie feeding contract that we've written until now? The attack vector can be external dependencies. In lesson 2, we had hard coded the CryptoKitties contract address, this address right here. What if there is a bug ever in CryptoKitties? If there is a bug in CryptoKitties, this buggy contract code is in your smart contract forever if you've deployed it. Hence, it makes sense to make this more configurable. Can you think of how you can do this yourself? I'm going to I would urge you to pause and think of how you can do it yourself. They will ask us to do this something similar. So if you look at the put it to the test section, here it says delete this line of code. Why? What are we trying to do? We're trying to make sure this is not hard coded in our contract so that when it's put there, it's there forever. We're trying to make it configurable so that it can change. How? That's what we're supposed to do here. First thing, remove this hard coded contract. Sounds good. Second thing, change the line where kitty contract, we created the kitty contract to just declare the variable. Do not set it to anything, okay? The kitty contract variable, let's not set it to anything because initially we don't have CK address because we have not hard coded it in our contract. All right. Create a function called setKittyContract. Can you guys think where we're going with this? Also increase the font size here. It will take one argument called the address. And finally, what will it do? It will simply set kitty contract equal to kitty interface of address. Cool. So what have we done? We've made kitty contract this variable configurable. So this can be changed by calling the set kitty contract address function. Let's see if the answer is correct. Feel free to pause and marinate this yourself. There is an error. This is why you shouldn't code at 12:50 a.m. Let's see. Delete the line of code. We did. Change this declaration. Don't set it to anything. That's what we did. Create a function called setKittyContractAddress. It will take one argument called address, and it should be an external function. That is the one thing we haven't done. What does external mean? It means it cannot be called from inside, but can be called from outside. Your users can call this, but you cannot call it somewhere here from inside your contract. That's what external means. And inside the function, we just set this to this. Why external? Why not public? We'll come to very soon. They're like reasons, gas optimization reasons, where it is good to make a function external if you don't want to call it from inside the contract. Hence, we've made this external. Try again. Seems to have worked. Chapter 2, ownable contracts. This is where OpenZeplin comes into the picture. So there is a very famous GitHub project here that you can go to. It's called OpenZeplin. The organization is called OpenZeplin. The project is called OpenZeplin Contracts. A few very smart people have written a bunch of Solidity contracts and open sourced them. And the community, a bunch of auditors have actually audited this code. Audited basically means they have checked that the code does what it says. For example, if I go to contracts here, you will see a bunch of different types of contracts. For example, finance. It has a vesting wallet contract, and you can read what it does. It handles the vesting of Ethereum for a given beneficiary. If you want to send someone Ethereum every few days, I think this is what that does. I could be wrong. You can actually read this contract thoroughly and see it says what it does what it says that it does. The second part, the next video, is going to be going through some of these contracts and trying to understand them. But for now, we will be using a very simple contract of theirs. They have a bunch of contracts. You can go through them. Each solves a different use case. There is one use case that we need in our zombie contract, which is what we're going to yoink from here. By yoink, I mean just copy paste from here. That use case is called the ownable contract. They have a contract there called ownable. Let's see what it does. It says here the setKittyContractAddress, which is the function we had defined in the last section, is external. The problem is anyone can call it, which means you can call it, I can call it, some rando can call it. When they call it, what will happen? They can change the address to some buggy address. So this should probably be protected. This function should only be allowed to be called by some admins, or more specifically, maybe the person who deployed the contract. The person who deployed the contract is the only person who should be allowed to call this function and hence change the contract address. Let's see how we do that. Comes into the picture OpenZeplin's ownable contract. This is a slightly older version of it because CryptoZombies is sort of outdated. You can look at the current most popular, most latest version on GitHub. But for now, we'll just read through this. So this is a contract very similar to the contract that we're writing. Let's see what fields it has. It has a private field called _owner, and in the constructor, which means this thing, the constructor is called whenever someone deploys a contract. You can, up until now, we've just written contracts. We haven't deployed them on Ethereum, which is similar to if in the Web2 world, deploying it on AWS. When you deploy it, the constructor is called for the first time. It's like similar to constructor in classes. And here we set the owner variable to message.sender, which means the person who's deploying the contract. Why is this cool? You also emit an event, which feel free to ignore for now. Why is this cool? This is cool because now forever on the blockchain, _owner is a variable that is set to the person who deployed the contract. If I deployed it, it's set to my address. If you deploy it, it's set to your address. This is cool because amongst the many functions it exposes, for example, the owner function that gives you the current owner. It exposes something called a modifier. Modifier only owner. What is a modifier? This is where I introduce something new. A modifier in Solidity is similar to middlewares in TypeScript, Express, HTTP servers. A middleware over there is a place that gets called before your actual logic is called. If you, in a Web2 world, ever make an HTTP call, this is your server, and you make an HTTP call. Let's say this is the HTTP handler. If you have a middleware there, and you've registered the middleware, let's say M, above the HTTP handler, first M gets called. M does a bunch of checks, and only if M says we're good to go does the control reach the main logic. Let me make this slightly cleaner. This is your request handler. This is a middleware. This is your end user. They send a request to your HTTP server. The request before going to the final request handler goes here to the middleware. The middleware usually does some authentication checks. Only if the middleware says, okay, we're good to go, does the control reach here. For the people in the full stack course, it should be fairly straightforward. For everyone else, if you don't yet know HTTP servers, Web2 world, it's fine. Feel free to ignore this part. The thing to know about this is, we can write, this is similar to a function. It's just a function. Only thing here is, after you do a bunch of your checks about whatever this modifier is supposed to do, which in this case, this modifier is supposed to check whether or not the owner has called a function. Let's say this was a function. Assume this is a function which says, okay, some logic should be run only if the person who's calling the contract is the admin. I repeat, only if the owner calls this function, assuming this was a function, should this logic run. Assume this, there's not underscore here, there's some logic here. So what will you do? At the very top, you will put a require. Require is owner. What is owner? It's a function that checks if message.sender equal to the owner variable. Cool. So after this require, if this was a function, if the contract is being called by the admin, control will reach here, else it won't. The modifier is very similar to a function, only it can be used in multiple places. It's like just one time you define, okay, what checks do you need to make? And under what conditions should the final function proceed? What is the final function? Only owner can be used in conjunction to a bunch of functions. Whenever you have defined a function, here you can basically put modifiers, similar to how you put middlewares in HTTP servers. In an HTTP server, in a request handler, you put a middleware. In Solidity, in a function, you can put a middleware or a modifier here. So if I write only owner here, what will happen is, before this function is called, control will reach here. Only if control reaches this underscore will all this logic be called, else the function will crash somewhere above. Cool. So that's the significance of underscore. What is this thing? It's called a modifier. What does it do? It gives you a variable that you can use in front of other functions. And before this function is actually called, before control ever reaches here, control first reaches here. A bunch of checks happen here. This is one modifier. We will define a few later on. A bunch of checks happen here. If all of them succeed, which means if in this case is owner is true, this required does succeed, then the control reaches here. And underscore basically means, okay, go into the function where the modifier was put. And hence only if this is an owner will this function be called. That's the significance of modifiers. You can define multiple modifiers of your own. This is just one. Why is this useful? We'll see in our contract. What was our original problem? The original problem was the setKitty contract address is external, which means anyone can call it, but we want to restrict it only to the owner. So what can we do? We can somehow extend this contract. If we extend this contract, what will happen? We will get all of these constructs in our contract, in our zombie factory contract. And then I can use this only owner modifier in the functions that I want to protect, in the functions that I want only the admins to call. Cool. Let's scroll down. Let's see. There are a bunch of other functions here I'd urge you to go through. Renounce ownership to renounce ownership. The admin is like, I don't want to be the owner of this contract anymore. And owner is set to a null address. Why is this cool? Because then you know for sure the CK address cannot be changed. Or like any function that is protected by this modifier can no longer be changed if the admin ever calls renounce ownership, because they have renounced the ownership. What is happening here? Owner is being set to a null address, which can never interact with the blockchain. Similarly, transfer ownership. If I am the current owner, I want to make someone else the owner, I can call this function and send the new owner in the address. And then this transfer ownership function will be called, which sets the owner to the new owner. So if you read through it, it's very basic sort of logic. Just feels complicated. Solidity is some big thing. It's actually fairly simple logic. And like amongst the many contracts here, if you understand all of them in OpenZeplin, actually pretty solid as an engineer, because you understand most of the finance contracts that are present here that hold like millions of dollars in value. Cool. Alrighty, let's put it to the test. What does it say? It says first thing, import ownable. Let's do that. They've already brought the ownable contract here. So import dot slash ownable. Secondly, modifier code to import, modify zombie factory to inherit it. So is ownable, because ownable is the name of the contract here. What will this do? It will bring all these functions and all these variables here. It's like inheriting. And why is that cool? That's cool because zombie factory now has access to the only owner modifier, which is this thing right here that we will use very soon. Cool. All right. So these are the two things it expected us to do. We've done it. Feel free to pause. And there is an error here. Needs to be ownable.sol. Good to go. Next chapter. The only owner modifier. So here is where they've introduced modifiers. I think, yeah, feel free to read through this on the website. It basically says the same things. I told you it's just like a function, only it's actually a middleware, similar to middlewares in HTTP servers. Does some checks, and only if those checks succeed does a function get called. In our case, it says the set kitty contract address, which is this function right here. We want to make sure only owners can call it, and hence we add this only owner construct. So here try to marinate why modifiers are cool. Modifiers are cool because I just had to add one variable name and this function is now protected. Versus if I had to do this check, I had to first like put an owner variable here. Once I'd done that, I would have had to put require here. And then if there are 10 functions that require them to be protected, I would have had to put require everywhere. This is okay if there's just one line of code in the modifier. If your modifier is more complicated, let's say it has 10 requires, it needs to check a few things. You need to put 10 lines of code here. You need to put 10 lines of code in another function that's protected. So that's why modifiers are cool, because you put all the logic somewhere. Now you might argue, Harkiyat, I could have just created a function and then done the same thing here. I would say yes, that is true. You can create a function that does the same things as the modifier, doesn't have an underscore at the very top. And then you can just call the function here. That is true for middlewares as well. So it's hard to argue why even create a new thing called modifiers and not use functions. But this is the clean, right, appropriate way to do auth checks before you want your final logic to be called. And the reasoning that's given behind why my middleware in HTTP servers is cool or required and why modifiers are required here is because your central logic remains separated to your auth checks, which are in a different function or a different modifier. Cool. Alrighty, I think this is good enough for this one. Indeed it is. Let's move on. Great. Now let's understand a few gas optimization techniques. First of all, what is gas? In Ethereum, you might have heard Ethereum is very expensive. At the end of this video, since I've already shot it and I'm reshooting this part, I know that we're spending $60 to deploy our contract on the Ethereum blockchain. So it's actually very expensive to deploy something on Ethereum because Ethereum is a very used blockchain and like compute there and resources there are very limited, and a lot of people want to put their contracts there, make contract calls. And if a lot of people are competing against each other, you have to pay more gas. Ethereum, if you want to send a transaction there, which means I want to send someone Ethereum, I want to make a contract call, I want to deploy my own contract. All of these require you to compete with a bunch of people all around the world who are competing to put their transaction in, because the number of transactions that happen on Ethereum in a second are very less. I will repeat, Ethereum does not support a lot of transactions per second right now. You can actually go to etherscan.io and see all the transactions that are happening in a block. So if I go here, you will see 15 seconds ago, a block was created. 27 seconds ago, another block was created, which means in 12 seconds, this one block was created, which has 124 transactions, which means there are around 12 transactions that are happening per second. So if you are one person who wants to put their transaction, there are a bunch of thousands of people out there who want to do the same. You guys have to compete against each other and pay what's called gas. Why is it needed? It's needed because this gas is what secures the Ethereum network, what incentivizes node providers throughout the world, miners throughout the world who are bringing up ETH nodes. So this is a fundamental concept of all blockchains, not just Ethereum. And what does it say? What does it do? Anytime you're making a transaction, you have to send something extra with that, some ether in it, which is like native Ethereum token, or like if you go to CoinMarketCap, basically one ETH is worth $1,850. So you have to buy some ETH, and if you want to make a transaction, you have to send some ether with it. This is just the way blockchains are built and the incentivization mechanism in blockchains. Cool. Now, That's what this section mostly says. Now it tells you a few things on how you can save gas. You're writing contracts, and in the end, these are going to be function calls that your friends, people around the world make. If your function is too complicated, too long, then it will require more gas. The more compute it will require, the more gas that function call will require. The more storage you do in a function call, the more gas it will require. The two expensive things on a blockchain are storage and compute. Why? The blockchain is effectively the copy of this data throughout the world. If you deploy a contract, let's say the zombies contract, someone calls create zombie function, a zombie gets created. This data is stored in thousands of machines, not one. Why? Because that's what blockchain is. That's how it sort of makes sure that if one node goes down, the whole network does not go down. So the data needs to be replicated. This is why the more data you store, the more gas you have to pay to incentivize all the miners. And the longer the function, the longer time someone has to run that on their machine, that specific function. Hence, you need to send more gas. That's just the way the blockchain is written. But you can do a few things to optimize your contracts so that when your end user calls a function, less gas they have to spend. Let's see what those are. First thing is called struct packing. It says there are a few types of uints, right? Uint 8 bits, uint 16, uint 32. Based on how many bits you're using, that big. If you want to store a very small number, you will use uint 8, which means something that's less than 2 raised to the power 8. What is 2 raised to the power 8? It's basically the maximum number you can store in an unsigned integer that has 8 bits. If this was too complicated, don't worry about it. It's just some maths around. What does uint 8 mean? What does uint 16 mean? What does uint 32 mean? It basically means how big of an integer you want to support. And you can use any of these uint types in your contract. But it says normally there's no benefit to using these subtypes because Solidity reserves 256 bits for all storage regardless of the uint size. So it doesn't matter if you put uint 32 here or uint 256, you will still use the same space because Solidity reserves 256 bits irrespective of what you're using. However, there is an exception inside structs. If you have multiple uints inside a struct, using a smaller size uint will allow Solidity to pack these variables together and hence take up less storage. So if you're using a uint 256 here or uint 32 here, there is no difference. Let's say there's a variable here. There's no difference between this and this when it comes to saving gas. But if you have a struct, then there is a big difference if you go from uint 32 to uint 16. And this is what's called struct packing. Okay, let's put it to the test. In this lesson, we're going to add 2 features to our zombies. So what features does our zombie right now have? It has a DNA, it has a name. It wants us to add 2 new features. The first one, a uint, and what is it called? Level. I think this will start from 0, 1, 2, 3, 4, keep going up. And finally, ready time, which we'll see where it comes into the picture. All right. Both of these are uint 32s. And now since we've specified uint 32 and by default, I think it's uint 256, we have saved some space. We know the level won't ever go beyond 32 bits. Same for ready time, which is why it makes sense to explicitly specify 32. If we would not, it would default to 256. And hence, what have we done? We have saved some space or some gas for our end user. 32-bit is more than enough to hold the zombies level and the timestamp. Cool. So this will allow some gas packing data because the regular uints are 256 bits. Cool. Check answer. Good to go. Time units. So in JavaScript, there's this global variable called date. If I go here and do new date, it gives me the current date. Then you can do a bunch of things to get like the Unix timestamp or like the month, so on and so forth. Similarly, Solidity gives you something similar. The level property is self-explanatory, but the ready time requires a bit more explanation. The goal is to add a cooldown period, an amount of time the zombie has to wait after feeding or attacking someone before it's allowed to feed or attack again. Basically, when someone feeds their zombie or attacks the zombie, we want to make sure they are not able to call that function again for some period of time, which is why we need some time constructs here. Okay, let's see how they explain this. The variable now will return you the current Unix timestamp. For those of you who don't know, Unix timestamp is basically the amount of seconds that have passed since one date in 1970, I think 1st January 1970. So if you go to your browser, click inspect, and here write new date.getTime, This is the amount of milliseconds or seconds, one of these two things, that have passed since 1970, 1st January 1970, I think, or some date in 1970. This is the standard that's used all across in computers, a number that's called the Unix timestamp to represent the total number of seconds that have passed since a certain time point. Cool. The way to get that in Ethereum is the now variable. Alrighty. Solidity also contains certain time units such as seconds, minutes, hours, weeks, and years. These will convert to a unit of the number of seconds in that length of time. So example, 1 minute is 60 unit. If you put unit A equal to 1 minute, what will A hold? It will hold 60, so on and so forth. If you put 6 hours, minutes, it will just be the number of seconds. Cool. What does it say here? Here is an example of how these time units can be useful. Updated time. If you ever call the update timestamp function, you can set last update to now. And then there is another function called 5 minutes have passed, which checks if now, which means whenever this is called, is greater than last updated plus 5 minutes. I hope you're getting where we're going with this. This is what we'll use in our cooldown logic. We want the end user to only be able to call a function like some specific function, like the feed function, once every 5 minutes, let's say. So what can we do? When the user calls the feed function, we can, after we've done the feeding, we can set last updated to now, which is the last time this function was called. At the top of the feed function, we can put a check like this, which checks ki 5 minutes have passed since the end user has made the call. So that's what we have to do now in this contract next. Let's see what it asks us to do. It says declare a unit here called cooldown time and set it equal to 1 days. Unfortunately, you have to write days in Solidity. You can't write a day. So even if it's one or many, you have to use plural. Second, we have to add a level and ready time field to our zombie when we create the struct. So when we were creating the zombie, we were pushing name and DNA. We also need to put a level, which is one for level. So we want the user to start from level 1 and uint 32 of now plus cooldown time, which means when the user creates a zombie, their ready time becomes the current time, which is the time that they've created the zombie, plus the cooldown time, which means they cannot call the protected functions, the functions where we will put this sort of a check for another cooldown time, which is another 1 day. Hope that makes sense. After the person has created a zombie, that zombie won't be able to do a few functions, a few things for a day, because that's what we're storing in the ready time variable. And later on, we'll sort of protect the functions by checking if ready time plus 1 hour has passed. Okay, cool. I think that's all it asks us to do in this one. So feel free to pause here. What have we added? Updated the zombies.push and added a cooldown time here. Check answer, good to go. Zombie cooldowns. Now that we have the ready time property, let's jump to zombie feeding.sol, which is this function which had the feeding functions. We're going to modify feed and multiply such that feeding triggers a zombie cooldown. Okay. Feeding triggers a zombie cooldown. What does a zombie cooldown mean? We just need to update that zombie's ready time. And zombie can't feed on kitties unless their cooldown period has passed. All right. The two things we have to do. Make sure whenever this gets called, ready time is updated. This can only be called if a few minutes have passed, or specifically 1 day has passed since the last time this was called. All right. One thing it says here is you can pass storage pointers to a struct as an argument to a private or internal function. This is useful when you want to pass a zombie around that you want to update. If I define a function and if I put a zombie as an argument to the function, if I define it as a storage variable, any changes that I've made here will be put on the blockchain forever. That's what storage means. Why? We'll come to very soon. Put it to the test. Let's define a function. Let's call it _trigger cooldown. It will take one argument. Okay. A zombie storage variable. All right. The function should set zombie.readyTime to again now plus cooldown time, because whenever this is called, we are triggering a cooldown, which means we are setting ready time to current time plus cooldown period, so that whoever uses ready time knows कि भाई अभी cooldown time तक for 1 day don't use it. Don't let the user call this function because the user called this function in the last one day, at least once. Cool. That is what updating this variable does. Next, create a function called isReady. It also takes a zombie as a variable argument, I think. And what will it do? It will be an internal view function. It will return a boolean. Okay. Returns bool. The function should check if return zombies.readyTime is less than equal to now. If zombies.readyTime, if now is greater than zombies.readyTime, zombies.readyTime is when this zombie is ready to be called on a function again. If now, whenever this function is called, is greater than this, that means we're good. This returns true. However, if now is less than this, which means if this is the cooldown time and currently we are here, then we shouldn't allow a function to be called. Hence, this returns false. As time passes by and now becomes more than the ready time is when you're good to go and this returns true. And then we'll later see how we use this function. For now, we've just defined the two functions. This one updates the ready time. This one checks if current time is greater than the ready time. All right. Feel free to pause. There is an error. Sure, I'm returning something incorrect. Or might just be a semicolon. Might just be a semicolon. Try again. Maybe something more. Put a return here and trigger cooldown function. There is a typo here. Okay, hope you guys saw this before me. Function trigger cooldown takes zombie storage as a variable. Zombie.readyTime equal to now plus cooldown time. You int 32 of that. I hope you guys are paying more attention than me. Function body should set this to this. Create a function called isReady, which is this function right here. Takes zombie storage argument zombie. It will be an internal view function which returns a boolean. It simply return this. Now it seems like this should be good enough. Show me the answer, sir. Missing something obvious, hopefully. The first function is also internal. Good to go. Public functions and security. So now let's modify this to take the cooldown timer into account. Okay. Looking back at the function, you can see we made it public in the previous section. We made what function public? The feed on kitty function, I think. An important security practice to examine all your public and external functions and try to think of ways users might abuse them. For example, earlier we used the only owner modifier in a few places to make sure the kitty contract can only be updated by a few people. Re-examining this particular function, the user could call function directly and pass this and this to it. The feed and multiply function, is a public function, which means your end users can call it directly rather than calling feed on kitty and passing some random species here. So they say this is one thing. This is one function that should only be called from within your contract. In the future, you could have a feed on dog function that also calls feed and multiply, but you need to make sure your end user cannot call it, which is why this should probably not be public. It should be private, internal, what we'll come to. Put it to the test. Currently, feed and multiply is a public function. We should make it internal because it needs to be called from here. We don't want a user to be able to call this function with any DNA. That sounds right. Let's make feed and multiply take our cooldown time into account. First, after we look up the zombie, which is right here, we should add a require that makes sure isReady returns something true. We should add a require that checks isReady, which means whether or not this zombie is ready to the ready time. The current time is more than this zombie is ready time. Cool. And if it isn't, that isn't the case, which means let's say our end user is spamming this function, the control will reach here and it will stop because the ready time will be less than the current time. The current time will be less than the ready time. Cool. How will that happen? It will happen if I trigger a cooldown here. I think I have to pass this zombie both the places. My zombie. So what have we done? 1, I made this function internal. 2, I made sure this logic that actually changes the zombie, creates a new zombie, only runs if this specific zombie is ready. And finally, If we do create it, which means this zombie was ready, we make sure we trigger a cooldown for it so that this function cannot be called again for another day. Cool. What does trigger cooldown does? It says ready time to be current time plus cooldown time. Our cooldown time that we defined was 1 day. So for the next 1 day, this function can no longer be called. If someone calls it, control will stop right here. Alrighty. Let's see if this worked. Check answer. Good to go. More on function modifiers. So the thing that they've explained here is that modifier can also take in arguments. It's not necessary that a modifier is a plain old function that you can call. Any modifier can also take arguments, and then you can do checks on these arguments, and only if they succeed will you call underscore, which actually sends the control to the next function. All right. Let's see how they want us to use this. They say in the zombie helper function, so they've created a new zombie helper class which extends the old zombie feeding class. Create a modifier. Okay. Modifier, let's call it above level, and it'll take 2 arguments. Okay. A uint called level and a uint called zombie ID. The body should check and make sure that zombies of zombie ID dot level is greater than equal to level. And only if that's true should we return this underscore. All right. Seems like we're good. I think that's all that's needed. We've just defined a modifier. We've not used it anywhere. What does it do? Based on the current level, the level variable that you're sending, and this zombies level, it makes sure that the actual function will be called if this zombies level is greater than the level that you're passing in. How do you pass in these things? We'll come to very soon. Let's see if this works. There is some error. Create a modifier called above level. Modifier, older range. What are the 2 arguments it takes? Level, which is a uint. Zombie ID, which is a uint. Body should make sure. It should make sure. Means it should require this. Hai ki nahi? All right, good to go. Zombie modifier. Now let's use the above level modifier. Okay. Our game will have some incentives for people who level up their games. Now the level is initially 1. It remains 1. There is no way to update it yet. But there will be a way in the future to increase your zombies level. Until we reach there, we have to just define a few functions that only run if the zombie has some level. For zombies for level 2 and higher, users will be able to change their name. For zombies for level 20 and higher, users will be able to give them custom DNA. All right. Seems like 2 very weird use cases. Again, supposed to sound weird. Let's first just understand creating custom modifiers and using them. All right. We'll implement these functions below. Here is a code from the previous lesson. All right. Don't really need it. We'll do it ourselves. Put it to the test. Create a function called change name. Alrighty. It'll take 2 arguments, a uint zombie ID and a string memory new name. But something special here. It says not memory, call data. What is call data, Kirat? I'll explain very soon. It is an external function. It should have the above level modifier and it should pass in 2 for the level and zombie ID for the zombie ID. Where does this thing come from? It just comes from here. So one special thing to know here is whenever you're adding modifiers to your function, whatever arguments you're passing here can actually be copied from the argument list of the function. If your function has an argument, you can use it here. That argument will be as it is passed to this modifier. And secondly, you can put any variable here, which we have 2. Now we've created our own modifier, which accepts 2 arguments, and we have also called that modifier here. Alrighty. What is the next thing it asks us to do? It says first we need to verify that, which means require message dot sender equal to zombie to owner of zombie ID. Alrighty. Then the function should set the name, update the name for the zombie equal to the new name that the user has sent in the arguments. I think that's good to go. And finally, another function called change DNA. The arguments that it takes is the same as the function above, only rather than getting a new name, it gets a new DNA. So uint. It is external And we need to make sure only people who have the level 20 are allowed to call this function. All right. What does this function do? So the zombie DNA, I think it should require as well, and then just set the DNA to the new DNA. All right, we've added a lot of code here. I worry this might not work in the first go. So let's quickly verify. A function called change name, arguments, zombie ID, string, call data. What this is, I'll explain very soon. External, and it should have the above level modifier for 2 and zombie ID. Sounds good. Require, and then zombies of this thing called this. So yeah, so this is logically right, but I'm sure I've missed something. Oh, I haven't. Wow, beautiful. Alrighty. Bro, how do I make this go away? All right. So this is what we wrote in the last section. I want to quickly explain call data. So, bro, am I sharing my screen? Thank God I am. So call data, there are 3 things we have learned. 2 things we learned until now. Third thing came right now. We learned we learned memory, we learned storage, and now there is this call data thing. What is this and how is it different from memory and storage? So whenever you are passing these arguments, they can either be a storage, memory, and the new thing that we learned, call data. There are some differences in these. Storage means whenever you pass in a storage variable, you know, okay, if you change that variable, it will change on the blockchain forever. And this is the difference between storage and memory. If you change a memory variable, it is never persistent on the blockchain. It's just that you're changing that variable in memory here in the function body, which is why the gas used usually for a memory change is much lesser than a storage change, because a storage change is propagated on the blockchain forever. So if you have the choice between these two and you know the variable you don't want to change, or even if you want to change in a function body, the change doesn't need to be propagated to the blockchain, you use memory. But then comes this third thing called call data. Now what is call data? Whenever you know there is a function and that function is external, rather than using memory here, you should use call data. Why? Because this is much more gas efficient, because this is stored in a different place in memory whenever this function is called compared to memory. Call data is basically stored in the call data in ETH storage, which is like some long, very abstract concept I'm happy to explain. Long story short, whenever there is an external function, if you know a function has a variable that you don't want to change and don't want it to be persisted, you should simply use call data and not use memory. The benefits that you get from a function being external, the gas benefits versus let's say public, sort of go away if the variable that you've passed in is memory, which is why call data can never be used as an argument in a public function. It can only be used in the external function. Cool. That is good enough to know at this point the difference between call data and memory. And memory and storage is fairly straightforward, and storage and call data is also fairly straightforward. Alrighty. Storage is expensive. One of the most expensive operations in Solidity is using storage, particularly writes. This is because every time you make a change, it's written permanently on the blockchain forever. Thousands of nodes all around the world need to store that data in their hard drives, which amounts to data that keeps growing over time. So there is a cost to doing it. Alrighty. In order to keep this cost down, you want to avoid writing data to storage except when absolutely needed. Sometimes this involves seemingly inefficient programming logic. For example, rebuilding an array in memory every time a function is called, instead of simply saving that array in a variable for quick lookups. Too much data here. So let's try to break this down. Have you guys ever seen that algorithmic problem that says, okay, you have an array 1, 2, 3, 5, 7, 8, and you have to tell whether or not how many even numbers are there, how many odd numbers are there. How would you do it? Let's say there is a function called isOdd. When this function is called, it should return, sorry, not isOdd, maybe the function is called countodd. Function countodd, which needs to return number of, do some operations and then finally return the number of odd variables here. How would you do it? You would say I would iterate over the array Harkirat in a for loop and then increase the count variable based on odd or even and then return it. I would say sounds good. What if I tell you this can be modified? There's another function that can modify this. which means add more elements to it. And then we need to still call count add again and again. So there are two functions. There is the count add function and there is the add to array function. If I tell you there are these two functions and we would randomly call this function and this function, how would you change the logic of count, not add, but odd? If you know algorithms, what you'll say is, Harkirat, I will create a global variable called count of even or whatever odd, initialize it to 0. Anytime an element is added to the array, here I will change the value of count of even. And then whenever odd function is called, I'll simply return what? Count of even. Hopefully my bad handwriting does not sway you away from the actual logic of the two functions. This function, whenever add to array is called, you do push something to this global array, but you also change this count of even global variable. And secondly, whenever count odd function is called, you simply return count of even, this variable right here. Why is this cool? Because now you don't have a for loop here in the count odd function. So the time complexity of this function has been improved. The problem is on the blockchain, time does not matter at all for a view functions. View functions are completely free. If you have a view function, if a user calls it, irrespective of how computationally expensive it is, it will be free. So if I told you, okay, this was a view function, does it make sense for you to store an extra variable on the blockchain? That means, because putting a variable on the blockchain, updating a variable on the blockchain is gas intensive. Calling this function, irrespective of how unoptimal it is, has zero gas, because let's say this is a view function. Hence, in the blockchain, many times you will see that memoizing into a global variable would have made your time complexity of a different function better, but you still avoid memoizing or putting more data on the blockchain. And you say, okay, this function is going to be unoptimal when it comes to time complexity because view. It is a view function, whoever calls it, there will be no gas here, versus memoizing it, storing it on the blockchain does require gas. So many a times in your blockchain journey, you will have this innate DSA ka wo, कि I want to optimize this function, but you shouldn't, especially if you're optimizing the function by creating something more on the blockchain. So between time and space, always focus on space on the blockchain. Space is much greater than time. If you guys can see this, yeah, space is much greater than time. When there's a big when here, when the time that you're increasing, or like the time inefficiency that you're adding is to a view function. If it is to a non-view function, the functions that are public and that are not view do require gas. So if you make it computationally expensive, that you won't save anything. But if there is a view function, make it as unoptimal as possible. If making it unoptimal decreases the space that you have to put on the blockchain, that's a good thing. Cool. All right. So let's see that in action now. The get zombies by owner function. Define here. Let's declare a uint memory array called result. Uint array memory result equal to new uint array. And what's the length? It is this thing right here, owner to zombies, owner to zombie count of this specific owner. This is similar to the way they've told us to define memory variables in Solidity. Alrighty. Secondly, at the end of the function, just return result. All right, sounds good. So until now, we've just declared an empty array and returned it. We've not done the logic to pull all the variables for this user to the results array. I would urge you to do it yourself if you're on Crypto Zombies right now. Check answer, good to go. Now let's write the actual logic. All right, what does it say? Declare a uint called counter. If you want to read through the things above, it basically tells you what for loops are and how for loops work in Solidity. Declare a variable called counter, set it to 0, and then declare a for loop. You int I equal to 0, I less than zombies dot length, I plus plus. If zombies to owner of I equal to owner, then do something. What should you do? add zombie ID to the result. Yeah, results of counter equal to I and then counter plus plus most probably. Yeah, that's good to go. So what have we done here for the people who don't already understand it? We created the results array. We iterated over all the zombies, the unoptimal thing. And then what did we say? Result of counter equal to I, which means the first time the control reaches here, result of 0 will be I. And we will do counter plus plus. The second time the control reaches here, we will set the 1th variable of result to I, so on and so forth. Why is this cool? Because slowly we are filling the results array so that all the owners that this user has, all the zombies that this owner has, get put in the results array, and then we finally return it right here. All right. Check answer. Good to go. Cool. So wrapping it up, feel free to read through this. We will just move on to the next section now. The fourth section, which will introduce payments. So one special thing about Solidity is that Solidity lets you, like not Solidity, blockchains in general, sorry, my brain isn't working. One special thing about blockchains in general is that you can send ETH on the Solana blockchain, Sol, like some native blockchain token when you're making a function call. Whenever you're making a function call here, you can send some Ether with it. That is what gives Ethereum so much functionality. You might say here in the Web2 world also we have websites and we have Stripe and Razorpay that let you do the same thing. I would say yes. But the thing about Razorpay, the thing about Stripe is there is a lot of bank regulations in place, and that's sort of the original thesis of these things. These payments should be free without any regulation, which is debatable whether it's the best thing in the world or not. But today, if you want to register on Razorpay, for example, you won't be able to sign up because the government has a regulation that no more payment gateways can no longer accept new users for a while. If you do register on Razorpay, they can ban you someday for some fraudulent activity, let's say. ETH prevents that. Also, money doesn't reach your bank account directly. If you pay for my course on my website, the money won't reach me directly. It first goes to Razorpay, stays in their bank account, and then gets processed for me. So there are like 2 days before it comes to me. That is why Ethereum is cool. On ETH, I can say, bro, I will give you access to my course if you give me ETH right away. The ETH will reach me right away, my address, and they will get access to the course. That is what we'll build in the next part, the last part. But the point to notice here is, or the point to focus on is, ETH and blockchains generally, smart contracts are not just functions that you can change or like put on the blockchain. You can also accept payments, which is what makes them very cool. And let's sort of build use cases like DeFi protocols and like other things that are popular today, other contracts that are popular today. It's only because contracts can hold ETH and contracts can accept ETH from end users when they're making a function call. How? You see here, using the payable modifier. So what is payable? Whenever a function is payable, user can send some extra ETH to it along with the ETH that they already are sending as gas. Other than the gas, they can send some more ETH, and you can find the value that they've sent in message.value. Why is this cool? Because you can be like, bro, I have a service, let's say a course, let's say a video call, whatever. That is worth 0.01 Ether. And you can say, bro, if you want that service, call this function. At the top, you can do this check, which is require message.value to be 0.001 Ether. If this is not true, control will stop right here. If this is true, will the control reach here? And the transfer the thing function is like where you have the logic to actually transfer the course access, the video call access, so on and so forth, which is what we'll build in the last section. All right. Let's see how they want us to use it. First, they say define a event called level up fee and make it equal to 0.000001 Ether. All right. Create a function named level up fee, level up. Set takes one argument, a event called zombie ID. Should be external, alrighty. Should be payable, alrighty. The function should require message.value to be level up fee, and then it should increment zombies of the zombie ID that's been sent level by 1. All right. So we defined a few functions that can only be called if the level is 2 or the level is 20. How do you increment your level? By sending some ETH. So that's the use case of a game now. You can ask users to pay, and only if they pay a certain value will their level be increased. Okay. So we accept payments, check answer. Some small thing I've missed here. I know this because now this is the first time I'm coding it. 0001 ETH. I think it's 001 ETH. Try again. Good to go. withdrawals. One important thing is, where does this ETH go, Harkirat? Whenever someone calls this function, the level of function and sends some ETH, where does it go? And the answer is it stays in the contract. Just like you have a public address, I have a public address. Contract also has a public address and it can store Ethereum. Question is, how do I pull that Ethereum out so that I can off-ramp it and convert it to money, send it for other use cases, things like these? How will the game developer of this zombie helper game pull that money out? And the answer is by defining a function that looks something like this. So what is this function? A withdraw function that only the owner can call. And what does it do? It sets _owner to be address typecasted uint160 typecasted owner. Where does owner come from? Owner comes from the ownable contract. And why the typecasting? The reason is somewhere here. It is important to note that you cannot transfer Ether on an address unless that address is of type address payable, which is why we have to do this thing right here. But the owner variable is of type uint160, meaning that we must explicitly typecast it to address. So that's why we have to do typecasting here, and we have to set it to an address payable. Only then can we call owner.transfer, which is this variable dot transfer all the balance that this specific contract has. So whenever you call a certain address, which is payable dot transfer, money from this contract will go to that user. In this case, we've send the complete balance. So all the money from that is held in this contract will go to the owner in this case. But if you put someone else's variable or like public address here, it will go to that person. All right. Let's see what it asks us to do. It says create a withdraw function, which should be identical to the withdraw function here. So I'm just going to copy paste and maybe fix the indentation. The price of Ether has gone up 10x in the past 1 year, keeps going up and down. It's $1 at the time this was written. Today it's $2. Future it could be more or less. It's a good idea to make this configurable. How do you do it? Define a function. We've done this many times now. Set develop fee. What does it take as an input? A uint fee, and is an external function. What does it do? Changes level up fee to fee. All right. So what have we done? Added these two things. Check answer. Missed something very obvious somewhere. External. Uses the only owner modifier. Yep, you want only the owner can change the level up fees. Good to go. All right. This is where we take a pause. You can finish this whole module if you want, but after this is where the use cases become a little weird, and the knowledge we have gained until now is enough for us to build real smart contracts. After this is a bunch of practice, which I would urge you to do if you want. I want to move to a real world contract now so that we're not stuck in tutorial hell and building a zombie game that looks weird, and it'll become really weird from now. Like you'll start doing zombie attacks, one zombie will attack another zombie. So it's great practice we want to do. And again, if you go through this, you might feel at a few points why we're doing this and you just have to stick through it. I want to move to the final contract here. Enough knowledge we have until this point about Solidity and the constructs we need to build a real world use case, which is what we'll be doing in the next section. So I'll see you there. All right, guys, welcome to the final bit. We're now going to write a smart contract of our own, a website of our own, a centralized backend as well. All the things that we've learned until now, we'll try to weave them together and build an actual real world use case. In crypto, it's very easy to get distracted and build very random things that no one uses. One such thing, like you might argue, is the crypto zombies game that we were building. But what we want to build today is something that has real world utility, at least for me. And you'll see very soon, like the contract might be like 50% of the work we do, and the rest 50% is writing the front end for it in React and writing the back end for it in Node.js. There is a GitHub repo linked in the description, and there are very nice prompts for you to do it yourself. I would urge you to try the assignment yourself and come back to the video if you get stuck. If you want to watch me do it, you can do that as well. Cool. With that, let's get right into the video and let's understand the assignment. So I have this course selling website, and as you can see, there are 3 buttons here. Buy now, pay in dollars, and crypto. You click on buy now, you get like a Razorpay pop-up after you log in. If you click on buy in dollars, you sort of get taken to this page that lets you pay. All of these payments go into my bank account. But this is very different from the pay via crypto option. When this website was created, pay via crypto takes you to a page where I've written a few things. I've basically said I have a Ethereum address, please send me 75 USDC or 0.05 ETH, which is like 75 USDC, to an address, and then mail at 100xdevs.com that you've made the transaction, ping me the transaction signature. I look at it manually, and then I add people manually to the course via admin dashboard. That's highly unoptimal, and that's the use case we want to solve. What we want to do is write a contract where someone can come. They'll call a function. Basically, when the pay via crypto button is clicked, they should somehow sign some message, and 0.75 USDC or some amount of ETH should get debited from their account and credited into mine. When that happens, I want to give them course access. So there are a bunch of moving pieces here. Again, all of this has been promptified and written here on GitHub. So if you go to github.com/hkirath/web3 bootcamp, you can go to part 1 Solidity easy, and the 4 parts are just things we've discussed until now. Part 5 DIY has the prompts for you to do it yourself. I would urge you to go there and do it yourself. If not, you can follow along with me. Cool. Let's get right into it, and let's just quickly understand what are the moving parts here. Let's actually just read what I've written here. The folder contains the code for yada yada yada. Finally, part 5 is what we're discussing. Part 1 to 4 we have already done until the video until now. Here we build our own Solidity contract to accept payments from a user. The project contains a simple contract that accepts payments. It emits an event anytime a user makes a payment. A front end where user can go, connect their wallet and make a payment. Now what is a wallet? We'll come to. Once the payment is made, the user is given access to the course. A centralized backend that watches the contract, and anytime a payment is made, it gives user access to the course. So this giving access, this process is actually done by a centralized server on AWS that is watching the contract. Anytime someone pays to the contract, it adds the user to the course via like an API call. So this process of manually people mailing me and then me adding them via click of a button is replaced by an AWS instance that's listening to the contract. And finally, this is actually not optimal enough. This is like a hard to do that you can read about later on and try to like tackle it. We will just be focusing on the first 3 parts. So we have to build a contract, a front end in React, and a backend in Node.js. You can go to part 5 DIY, and I've written prompts as to how you can do this. You can actually ask ChatGPT, it will help you out. I have already coded it, so I'm going to take you now through the contract. What are wallets? How you actually deploy a contract on the Ethereum network? What is the test network? If you don't actually own Ethereum, how can you use the test network to deploy it there and just test your app out? Cool. Let's get right into it. First, let's just quickly go through the contract that I've written. The contract is called course contract.sol. So if you go to the folder, there will be 3 parts: the backend, the front end, and then the contract itself. This is deployed, let's say on Netlify, Vercel, some front end hosting service. This will be deployed on AWS, but this will actually be deployed to the blockchain. We'll see how. If you click on it, let's first quickly go over the contract. It only has things we have learned until now, so it should be fairly straightforward for you to understand. It has the ownable contract. We've already discussed this many times now. I've just copied it from OpenZeplin and pasted it here. I can also put it in a different file. I haven't put it in a different file for some reasons we will come to later on. For now, we have an ownable contract. We don't have to go through it. The important thing is only owner, the modifier that we use to make sure that only the owner can call certain functions. Finally, we have the course registration Solidity contract, which is ownable, which means it has all the ownable properties. You will see 2 important things here. Course fee, which as you can see is part of the constructor. So when I deploy the contract, I will put a constant course fee there, and then that's the variable course fee on the blockchain forever. There's no way to update it. And payments, which is a public array of this payment struct, which has the address of a user that's paying, that's their Ethereum address, an email. Whenever someone is making this payment, they have to give their email, and they need to make sure the email is correct, else someone else will get access to their course, or if it's a faulty email, then they won't get course access basically. So they need to make sure that the email string is an actual email. We don't do email validations because they're very hard to do in Solidity. Finally, the amount that they paid, which in this contract is simply the course fee. So it will almost always be constant until we actually change the course fee and add functionality to do it. Constructor, as I said, simply sets the course fee. So when you're deploying the contract, I will set a course fee. Let's say in the future I have another course. I can deploy a different contract with a different fee and then have a different centralized backend listen to that contract. For now, we're just deploying one contract for my current full stack course. Finally, there is a function, the most important function, pay for course. This is what other users call. If you want to buy this course, let's say, you will call this function on the Solidity blockchain, how we'll come to. But once you call this function, and as you can see, it's payable, we check at the very top whether or not you have actually sent the course fee amount of ETH, which could be 1 ETH, 0.1 ETH, 0.001 ETH, whatever I decide. And if you do, then we push this to the payments array and we emit a payment received event. This is important. This is what our centralized backend listens to and then adds you to the final course. Withdraw funds is for me. Only the admin can access it. And what will it do? It will just send the money to me. So this money that you guys send to the contract will be stuck there and I have the authority to pull it out. If I don't have this function, that money will stay in that contract forever and neither will I, nor will anyone else be able to pull it. It's just in that immutable contract forever. This has happened in the past. So you have to be very sure there is no bug here. If there would be a bug, I won't be able to pull out my money. Cool. Finally, a function called get payments by user, that a user can hit to get all the payments that they've made. Ideally, the goal is you only buy this one course only once. Let's say a user made some mistake and bought it twice, they can track it here. Ideally, as I said, you should only buy it once. This can also be a UI feature, like whenever someone connects to our UI, we check whether or not they've made a payment already. If they have, we show them a button that says you've already purchased the course. Please go to 100xdevs.com and you should have access to the course content there. Get all payments is mostly for me, the admin, if I want to just get all the payments that people have made, just to make sure if I have an admin UI, which we will build, I can see all the people who have paid for my course. And then of course, on my main website, 100xdevs@gmail.com or like harkirat.classics.co.in, they'll of course be added so I can track it on this admin dashboard as well. But we will be creating an admin dashboard specifically for the people who have paid via crypto and not paid via these buttons that you saw. Sorry, this took longer than I was hoping. These buttons that you saw, just an admin dashboard to track from the blockchain who all have paid for my course, because this data is stored on the blockchain forever, specifically the payments array. Cool. Let's do a quick recap. What have we discussed until now? We have written a contract. Contract lets me, the admin, when I deploy, it lets me put a course fee, which is a state variable. It gives the user a public function called whatever pay, and then the user has to send some 0.001 ETH, whatever is the course fee, and only then will they be added to the payments array, and also an event will be emitted. Finally, user can track their payments. You have a function for that. The argument is the address of the user. Again, this is on the blockchain, so anyone can call that function. Even I can get the payments for a different user. That's one of the downsides of a blockchain. Anyone can call the functions unless you have like some checks in there. Our function is public, and then that means this function that lets people track their payments, anyone can call and pass an address as an input. How? We'll see very soon. Finally, an admin, not really an admin route, a route to get all payments, which is also frankly accessible by everyone. We can make it only owner, but it's fine. The data is on the blockchain, and this gives you some what are called like hype worthy credits. I paid for the course. You can actually prove it to your friend. How? You can ask your friend to go to the contract and then hit this function. When your friend hits this function, they will see your email there. So that's another like immutable thing that happens on the blockchain anytime you buy the course. Cool. This is one of those use cases that no one really needs and like people build in crypto. The actual main use case is the payment bit, and then that's it really. The payment bit, and then of course the centralized backend, this payment bit, and then the centralized backend that we will come to, that's listening to events on the Solidity event, the Solidity contract, like the blockchain contract actually. Cool. This is where we are at. Let's try to deploy the contract. So this part is going to be how once you have a Solidity contract, until now we had a Solidity contract on like the input box on Crypto Zombies. So we never really compiled it, we never really ran it. and like their compiler was what gave us a true or a false, like whether or not our submission was right. Now let's copy this contract and actually paste it somewhere where we can compile it, maybe deploy it on Ethereum and see how that's actually done in the real world. Cool. At this point, I would urge you to go to the Remix IDE. This is a web-based IDE, which means it's like Replit, only it does Solidity things. So you can put Solidity code here, compile it here, get errors, so on and so forth. The way to do that is once you go here, you'll see a folder structure on the left. There's contracts, there is scripts, there is tests, which are things we will come to later on. For now, the one that we need to worry about is contracts. You can put any number of .sol files here. We will just put one, and that I've already put here, called 4 course contract.sol. You won't see this. You will only see these 3 test files that they have on the website by default. You can go here, click on new file, and add a new file here, whatever you want to call it. For example, course 5_course.sol. Maybe in the right folder. I've been putting it in the wrong folder. You put it in the contracts folder. So go to the contracts folder, create a new file, and then maybe go back to GitHub, copy the whole thing, and then paste it in the .sol file. I've done the same thing. It'll give you a warning. Don't paste anything randomly from the internet. Maybe not even my code unless you've audited it. All right. So I've just pulled the code from GitHub, pushed it here on a file. At the top, we have the ownable contract. Below, we have the course registration contract. Now, on the left, you'll see a few tabs. Specifically, go to this tab that lets you compile the code. So this is the first time we've actually compiled Solidity code. What we were doing on Crypto Zombies wasn't really compiling the code, or like converting it down into lower level formats. For example, if you're in C, C++, you run the G++ command to convert it into a binary. Similarly, now we're finally converting it into some zeros and ones, some textual format. And you can actually see 2 things here anytime you compile the codes. First one is called ABI. It stands for Application Binary Interface, I think. And then the byte code, which, as the name suggests, is the code in bytes. If I copy this and paste it in the URL bar, you'll see a bunch of alphabets. So that's effectively this code converted down to bytes. What you see here in the second thing, ABI, is also a very important thing. You copy this and open it in, let's say, VS Code or WebStorm. You will see I've already done it in one of these folders. What that gives you is this representation in JSON of your contract. So your contract, for example, has a course fee as the input to the constructor, which is a uint6, which is of type uint6, and internal types also uint6. Similarly, let's say there is a function in our contract, pay for course. If I search for that in the ABI, you will see the definition of the function. It's basically giving the types of your function in a very nice JSON format. It's not giving the actual body of the function. Nowhere here in this file will you find any of this logic, but you will find the signatures of the function. Okay, what does the signature look like? What does the inputs look like? What does the output look like? Why is this cool? This is similar to a declaration file in JavaScript. If you've seen .d.ts files, they contain the signature of the functions of the whole file, don't contain the actual body. That's exactly what this ABI file does as well. If you look at it, it's just a JSON format of all the functions that are present and their inputs, their outputs, their types, so on and so forth. Why is this useful? This is useful if you're using TypeScript, then this file will give you the right types when you're calling some functions. Similarly, in Golang and Rust, it can help you auto-generate a lot of code, which if you don't understand what it is, don't worry about it. But this file is sort of very important. And as you can see, this is part of our code base also, both front end and back end. We'll come to why and where it is used soon. Cool. I have compiled the code. What do I do next, Harkirat? After you compile the code, you need to deploy it. Right now, you've converted it into bytes. You have the ABI. You haven't yet deployed it on the blockchain. The way to do that is this next section right here. You'll see a few things here. At the top, it lets you select where should you deploy it. Now you can deploy it on Ethereum mainnet. It will be really expensive, really slow. And when you're testing, you probably don't want to do it. Hence, Ethereum provides you with a bunch of what are called VMs, which are sort of faster, cheaper versions of Ethereum. They're like forks of Ethereum. They let you deploy contracts and test them. And if you fail, you don't have to pay money. That's the good thing. So it's like a more centralized version of Ethereum, and it's free. It's a fork of Ethereum that's running. So which one will you can select anyone. Usually I select Remix VM Shanghai. It gives you an account which has 100 Ether by default. So you can do whatever you want. You're really rich here. And now the important thing it gives you is this. It gives you a bunch of buttons based on your contract's ABI. Our contract's ABI has the inputs as course fee to the constructor. So whenever you're deploying, if you look at it here, it says input required, and then see Daisy. Before you're able to deploy, this sort of has a weird UI. Let me refresh. Go back to compilation. First select our contract, then go to compilation, compile it. You'll get the same ABI, same bytecode again. Go to the deploy section, remix Shanghai, put in a course fee, whatever you want the course fee to be. In my case, it was $75. So let's see what $75 to ETH is. Again, this changes every day, but let's say I want it to be this much ETH, 0.00054 ETH, or maybe a little bit lesser because you have to pay gas as well. This sounds a little wrong. Okay, 0.0035 ETH sounds right. That's like $70 and $5 for gas. So I want this to be my course fee because my course is valued at $75. I want the user to send me at least 0.0035 ETH, and not at least exactly that amount, and only then will they be allowed to the course. This is the constructor call. When I click on deploy is when my contract actually goes on the blockchain, and as we've discussed, these contracts are immutable. So be very sure before you click on this deploy button. If there is anything wrong there, it's there on the blockchain forever. In our case, hopefully things are right. There's just one small thing here. You don't send ETH as 0.0035 here. ETH has a bunch of small divisions. So one ETH is 10 raised per 18, what are called GUIs. 1 ETH to GUI, and it's 10 raised per 9, 1 billionth. The input here is either 0.0, it's in GUI and not in ETH. So similar to how we have centimeter, millimeter, so on and so forth. Let's say the input was 1 kg. I would be urged to put 1 here, but let's say the input that's expected is in grams, more specifically. When we're checking the payments here, message dot value equal to course fee. Message dot value is checked. The value that you get here is in GUI and not in ETH, so that if someone sells this like really small ETH, this isn't like 0.00001, it will be like 100 GUI or something like that. So the input also needs to be in GUI. If you want the input to be in ETH, then you need to, the check here needs to be changed to something like this. So that is one thing you need to keep in mind. Let me just confirm if this is 10 per 9 or 10 per 18. Although I'm pretty sure message dot value is in which unit? ETH. It's in way, correct. Way is even smaller unit. So just like 1 meter is, 1 kg is 1000 grams is 10 per 6 milligrams. Similarly, 1 ETH is 10 per 9 GUI is 10 per 18 way. And message dot value, whenever you get this message dot value, you get it in way. So the course fee variable needs to be set in V as well. Otherwise, you'll be comparing. On the left, it will be way, and on the right, it will be ETH. So this comparison will almost always fail, because you will tell the user to pay 0.0035 ETH. They will pay 0.0035 ETH, but it will be compared to this very long number because message dot value is this very long number. Cool. Hope that's clear. So effectively, what will the input to this constructor be? It will be 0.035 into 10 raised per 18, which is basically 35 followed by 15 zeros. So let's do that. 35 followed by a bunch of zeros, and then we're good to go. Now if I click on deploy, as you will see here, the contract deployed very quickly. Again, this is going on a remix VM Shanghai blockchain, which isn't really anything. It's something for testing for now. Eventually we will actually be deploying it on Ethereum testnet and then Ethereum mainnet. But before that, let's just, whenever you're debugging it in Remix, you are a lot of times deploying it here in one of these VMs and then interacting with it as much as you can. So now if you see, this is the contract that got deployed, which like theoretically, what does it mean here? It means there is a contract deployed on this Remix VM Shanghai, but the way to interact with it yet is just via these sort of GUI buttons. These buttons, again, you get from the ABI. Your ABI says there is a withdraw funds function. It says there is a renounce owner function, which comes from Ownable, and all these things. More specifically, the one that you're probably going to be interacting with is this one, or your end users will be interacting with this pay for course. Pay for course is the function that they will call, and they should also send some value with it, which this doesn't let you, which is why if I click on pay for course here, the transaction will fail because it will say, I was expecting a good error message here. I don't see it. But basically the control will reach where here, and we'll check if message.value is course fee. When you don't explicitly mention some value here, which you cannot, there might be a way to do it. From what I know, there isn't. So if you click on this button, which means if your end user sends the transaction to buy the course, unless they're sending this amount of ETH with it, it will fail. But this is like very fugazi. This is not happening on a website. So let's do it in the real world. Let's deploy it on Ethereum and see how it works. So at this point, I would urge you to get a wallet. A wallet is, you can go through the previous roadmap, and we've discussed what is a wallet, how you create one, and what are private keys and how you store money there. If you have not ever used a wallet, you will have to buy ETH, or in this case ETH, or in the later case Polygon, Solana, whatever, from a centralized exchange and send it to a wallet. A wallet is basically something like this. For example, this is a wallet that I have, Backpack, and it shows me the amount of sort of money I hold, and then ETH I have, so on and so forth. In this case, it's Solana. If I go to an Ethereum wallet, let's say, let me not do that. If you want to do Ethereum, you can do it in Backpack as well. If you want to do it in another wallet, MetaMask is another famous one. And that's what you see here. So this also, there are a bunch of steps to installing a wallet. At this point, let's take a pause and let's discuss what those are. If you want to install Backpack, go to backpack.app and put in click on downloads and download the Backpack extension and go through the steps to actually install it. Once you do, you will see Backpack here. Usually wallets are extensions like these. Similarly, if you want to install MetaMask, go through the whole procedure on metamask.app or like whatever the MetaMask website is, and then you should see a wallet that looks like this. Whenever you install these and select Ethereum, you are by default connected to Ethereum mainnet. That's what I am connected to here. So if you look at my tokens on Ethereum mainnet, which means how much actual money I have, this is actually money that people sent for the course through this unoptimal sort of scenario. You can see 150 sort of US dollars. That means 2 people sent Ethereum to buy the course, and then 150 USD coin, which means 2 people sent USDC, which is also a coin that sort of pegged to the dollar, and then USDT, 4 people sent. That's how this wallet sort of has this much Ethereum. This is not my personal wallet. This is my personal wallet, but I did not fund it. People who bought the course funded it. Now we're going to use this wallet to actually deploy things on the blockchain. You should take a pause here and install either MetaMask or Backpack or whichever wallet you're comfortable with, and maybe put some Ethereum in it. If you don't, you won't be able to proceed from here. There are ways to sort of use a test net in when you're doing these blockchain deployments or even like trying your contracts. Unfortunately, due to 1,000 reasons, it's not very easy to get testnet Ethereum. So unless you have actual Ethereum in a wallet, you won't be able to get testnet Ethereum either. So you will have to buy Ethereum on a centralized exchange and then move it to your wallet, and only then can you proceed. Else you can just watch what I'm doing here and you should be good to go. Cool. So at this point, just take a pause. If you want to install. If you want to buy some ETH, go try it and then move it to a wallet and then maybe proceed with me. Else you can just follow along with me. Cool. So I'm on Ethereum mainnet. This is the actual ETH that I own, USDC I own, USDT I own, but there is also a testnet called I don't know how to pronounce it, so I'm just going to call it the G testnet, where you can get these tokens for free. how do you get it? One, you have to go to MetaMask developer mode. You have to turn on developer mode. Once you do, you'll be able to see this testnet, and you can just search for testnet faucet. A faucet basically represents a place from which you can get free tokens on the testnet. They don't mean anything. These 0.02 G ETH that you see, they actually come from this faucet. The only problem is you cannot. So there are a few steps for you to get Ethereum. One, you should copy your public address. So this is the public address that you show to everyone. Your private key when you were trying to sign up on MetaMask, you should have seen there. You should keep it private, but this is your public key, and this you can give to the world. I'm giving it here, pasting it, and click on send me ETH, and it will send me some 0.02 ETH on the testnet, which has no monetary value. I've already done it once, so it's not letting me. It will let you do it as long as on the same address you have some ETH on Ethereum mainnet, which means you will have to put some 0.02 ETH, some minimal amount, and only then will you get testnet Ethereum, else you won't get testnet Ethereum. There are reasons why this is done, why we can come to in a future video. Like, it's just that people sort of steal this Ethereum, even the testnet Ethereum, even though it does not have any value. So you have to really gate it before you give it to people. That is why this testnet Ethereum that holds no value, also there are a bunch of steps for you to get it. I would urge you to choose some glass now and try to get it. Once you do, then you can with me deploy the contract on first the testnet, and then we'll eventually deploy it on the mainnet as well. The way to do that is change Remix VM to injected provider. Now, what is injected? What is provider? For this, you have to understand a little bit of how wallets work. Whenever these wallets like Backpack or MetaMask or like other wallets are basically a Chrome extension, and Chrome extensions have the power to inject some code in the website. So any website that you go to, Chrome can inject some JavaScript code in there. That's why they're called injected providers. And this is also why wallets are Chrome extensions or like browser extensions. The reason is when you create dApps, for example, we will be creating an app today, a dApp today, a decentralized app today. Basically a website that looks something like this, where people can come, put their email and click on a button. When they click on a button, the money needs to be debited from MetaMask, and this can only happen if MetaMask has some access to this website. Website can sort of ask MetaMask to debit some money. So these wallets hold your private key and connect to a website, have access to inject code in the website. And when you click on pay for the course, we can run JavaScript that can ask the wallet, okay, haan bro, please give me 0.01 ETH. Of course, there are checks in place. The wallet will actually ask you whether or not you want to proceed. We will see that very soon. But this is why wallets are sort of finicky, and they need to be extensions, because any dApp that you go to, any website that you go to, where you want to send Ethereum, buy some Ethereum, convert some Ethereum. For example, if you go to Uniswap, which is a website that lets you convert from ETH to Sol, let's say, this website needs to have some gated access to your wallet. So if you see here, this is my wallet. If I say, okay, I want to convert 0.0001 ETH to whatever Uniswap token or USDC token, when I click on the swap button, it should be able to ask MetaMask to debit 0.0001 ETH. That's why wallets are extensions and not websites of their own. Now, this is the way you do wallet management or private key management on a website. It's slightly different on a centralized backend. We will come to that later. But for now, as an end user, this is how your end user is going to buy your course. When they go to this website, they will click on the pay for course button. You will see a pop-up here in MetaMask or Backpack based on whichever one they have connected. And then they will have to approve the debit, and only then the debit will happen, and they will interact with the Solidity code on the blockchain. Cool. Quickly to recap all of this, we have a .sol file, which means the Solidity contract. Right now, it is present in Remix, the website remix.eth.org. It's not yet deployed on the internet or like on the Ethereum blockchain. What are we saying? We are saying to deploy it on the Ethereum blockchain, first create a wallet, put some ETH in it, because deploying a contract on a network requires some ETH, either MetaMask or Backpack or whichever wallet you want. Once you put some ETH in it, we will actually deploy the contract on the blockchain. And how will you pay gas for this transaction? You will pay it via your wallet. Cool. Let's see how that's done. Let's go to the remix ID again, and we selected injected provider here, which basically means MetaMask or Backpack, based on whichever sort of gets access. It's basically a race condition here. Whenever you have multiple wallets, ideally you should just have one, else they will compete with each other. Let's refresh the page. Let's go to our contract again. Let's compile it again. Let's go here. Rather than selecting remix VM, let's select injected provider. Once you do, you see the account here says 0.543, which is this account, and this 0.543 account is connected to the testnet, which means when I make this deployment, it will happen on Ethereum testnet. Ethereum has a bunch of networks. There is the main Ethereum network, and then there are these bunch of testnets, and there are a bunch of folks like Polygon. I wouldn't call it a fork, but like a bunch of other networks that follow a similar format, and a Solidity contract can be deployed to them as well. So a Solidity contract can be deployed to any EVM compatible blockchain. ETH is one. This Glory testnet that we're seeing, Goilery, however you pronounce it, is another one. Polygon is another EVM compatible blockchain, which is why a single contract can actually be deployed to different blockchains. Each blockchain has their own moat, and one is fast, one is slow. ETH is the most reliable one, which is what we'll be deploying to today. First, we'll deploy to its testnet, make sure things are good, and we'll deploy to the main website. All right. The way to do it is injected provider has been selected. Select your price. In our case, it was 3.5 followed by, I think, 15 zeros. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's the ETH that someone has to pay. And then you simply click on deploy. Now, when you do that, you will see a pop-up come here. This is very different from when we had selected Shanghai. On Shanghai, it already went because your private key is sort of stored here and you don't really have any ETH. Now, in this case, we're on testnet, so our ETH doesn't matter. But if you were on mainnet, it actually would matter. So before MetaMask actually puts this Solidity code on the blockchain, it asks you, okay, you will have to pay this much ETH. Are you comfortable paying it? Only if you're comfortable paying it should you confirm. It gives you an actual transaction simulation. So you should actually look at it. It says this is the contract deployment, and this might take around this much ETH in the current network to be deployed. So please make sure you're comfortable with it. I am comfortable with it, so I'll click on confirm. When I click on confirm is when I can now see a pending contract here. This is one of many sort of transactions that I've done. I've deployed a contract before this as well. I've received some ETH from that testnet faucet. When I deployed the contract earlier, I had done a contract interaction. So I've done a bunch of things here. Right now, we just deployed another contract. So if I click on this and I click on view on block explorer, something will come up here. This is my transaction on this website called etherscan.io. This is one of many what are called transaction viewing websites. A transaction under the hood is very ugly, but they let you see a transaction in a very clean fashion. So in our case, this thing that you see in the URL bar is called the transaction signature. Whenever you do a transaction on the blockchain, you get a signature which identifies your specific transaction, similar to, let's say, a transaction ID you get when you send money to someone on your bank account. This is the transaction hash. More importantly, what does it do? We have created a smart contract, and most importantly, this unique ID that you see is the ID of our contract on the blockchain. So this ID or this ID is the ID to identify our contract on the blockchain. This contract has a bunch of code in it that we had created, written here. It's not Solidity code. It's like some zeros and ones. Basically, the byte code that you saw here is what gets deployed when you're deploying a smart contract. And it's now stored here on the blockchain forever. Why is this cool? Because now other people can interact with it. Not necessarily people who are on this website or like I was able to interact before. Actual people through a website can interact with this contract. How, we will see very soon. A good thing to do after you've deployed a contract is post the contract code here on Etherscan. If you click on contract here, it will show you this is the byte code of this specific contract, which means the same thing that you saw right here. This byte code and this byte code is the same. But whenever someone comes here, they can't actually read the contract, which is not great, because before someone interacts with your contract, they would want to read as to what the code actually looks like. So if you are the owner of the contract, which in this case we are, you can verify and publish the contract. The way to do that is just click on the verify and publish button, select the compiler type, which in our case is the same thing that you see here, which is 0.8.18. And it's all code in a single file. This is one of the reasons I chose a single file to put the ownable contract and the other contract, so that we could just simply select a single file here. Let's select no license and click on continue. Now it asks us to put the Solidity code here. I'm going to copy this code. I'm going to paste it here. So this is sort of similar to open sourcing your code. I have a contract. I have deployed it. I am now publishing my actual code in it, which is like human readable code. And why is this cool? This is cool because once this completes, anyone can come to the contract and actually look at the actual code. How? Let's see. Let's go back to the contract. This was our contract code, and now you see anytime someone comes here, they will see contract and a tick. If you click on the tick, you can actually see the code. Now, whenever someone is interacting with this specific contract, they can come here, look at the code, make sure it does what you're saying it does, and only then proceed. So this is one thing you should always do when you have deployed the contract on a chain. Cool. We have this contract address. Now we need to start interacting with it. More specifically, we want to create a website where people come, and when they click on the pay for course button, they send the required ETH and make the transaction, so that this contract is actually being used in the real world. So this website is just a way for people to call functions on the contract. Another way might be a CLI, another way might be a mobile app, a desktop app, so on and so forth. So you can create multiple clients for this. We will be creating a website, but in the end, whenever you're deploying a contract, you want to create multiple clients, or like give users an easy way to interact with your contract. They can do it totally through code, but no real user will do it through code. You need websites for this. So this is the one that we're creating today. We no longer need this, if I'm not wrong. Yeah, I think we're good. We're done with this. We don't really need this. If you want to, you can still select injected provider here and like play with this contract that was deployed. This is one client to our contract. So this is the contract that's deployed. This is a client to the contract, which means I can call a bunch of functions here and see the input. A better client is a website, which is what we're going to build next. Cool. Okay. Let's maybe do a quick summary of what we've done before we proceed. The summary is we created a Solidity file, which is our contract. We installed a wallet, which is the most important thing here, which was either MetaMask or Backpack or any other wallet that you want. Then we deployed our contract where on the testnet, not on Ethereum mainnet yet. And before that, we also sort of airdropped ourselves some testnet ETH, which you can do if you have real ETH, otherwise you won't be able to. And finally, we put the contract on Etherscan. Why? So that other people can go there and now read the contract and be sure before they interact with our contract. Cool. Alrighty. Now let's create this website. Okay. For this, I introduce a new library here called Web3.js. Web3.js is one of many sort of libraries that let you talk to the blockchain. In the end, blockchain sort of exposes certain functions in a certain format that you can call from various languages, not just one. Effectively, these are just HTTP calls that happen under the hood. The one that we will be using today is Web3.js, but there's one in Android, there's one in iOS, so on and so forth. You can use these libraries to very simply call high-level functions that let you interact with the blockchain. Cool. Let's see how Web3.js lets us do it specifically for this website. So what does this website require? It requires some text, a course fee section, which it gets from the blockchain. This was my earlier contract that I deployed. It required only like really less ETH. Ours now requires 0.0035 ETH. And then finally an input box for someone to put their email and then pay for course button, which when they click on, they will on their MetaMask or their Backpack get an approval. And if they approve, money gets debited from their wallet, reaches our contract, and then they get access to the code from our centralized backend. First, let's build the front-end code, then we'll get to the centralized backend. So if you look at the front-end code, maybe let's look at it on GitHub. It's effectively a simple React app. Hopefully a few of you have done React. And if you look at the top level app.tsx, there is some magic that happens here, which I will come to. And then effectively we have two routes. The course registration route, which is this website right here. And I've also created an admin page. Again, this data is all on the blockchain. So anyone can actually see admin data, which effectively is who all have paid and like how much money you've made. but I've created like an admin page that the user can go to. Before we sort of get into the individual components, let's look at what I'm doing here. So I've actually put web3.js here in index.html. So if you go to index.html, you will see web3.min.js that I'm importing from Cloudflare. Now you can use an npm module and like import it and get better types in your React components. I specifically just used this sort of script that gives me global variables. Specifically, the two important global variables that I get are web3. Yeah, that's the only one. Window.ethereum comes from someplace else. I'll come to where. Maybe let's discuss that. So what am I doing here? When app gets rendered, the very first time, this is an empty array, which means the first time this gets rendered, this logic runs. Let's see what this logic says. It says if window.ethereum. Question is, what is this window.ethereum and where does this come from? If I go to my Chrome, click on inspect, go to console and write window.ethereum, I get nothing. But if I go to my Brave and I type window.ethereum, I get something and it says proxy here. Can you guess why I get it here on Brave and not here? Take a pause and guess. The answer is this thing right here. Backpack and MetaMask are what inject this thing into the DOM. This is what injection actually means. They actually inject a global variable called Ethereum. And I don't see it here because I don't have any wallet installed. If I install MetaMask on Chrome, I will see it here as well. That is why at the very top we do this check and we tell the user, please install an Ethereum wallet, and only then this will work, else the website does not really work for them. If they do have an Ethereum wallet, this very first function that I've written here, window.ethereum.request, is a button that requests MetaMask to be able to connect to this website. So any wallet has to be very sort of secure to connect to any random website. There are a bunch of random websites on the internet and you don't want your wallet to connect to each one of them, which is why the first time you come on a website, you want a pop-up like this that appears. If a pop-up like this appears, then the user can select, okay, does this look legit? Only if it looks legit will I select which wallet I want to connect and decide whether or not I want to connect. This line is what triggers that. It triggers that for the first time. Okay, if this user has a wallet, ask for their approval, at least for the first time. And when they click on connect, then I've connected to this website. Now in the future, I can just refresh and this will just work. But for the very first time, if I did not have this logic here, this website would never connect to MetaMask, which means it would not be able to. When I click on this, nothing would happen, or even backpack. So this line is super useful when you want your user to, when you know your user is on a website, you know they are going to send some transaction, some money needs to be debited from their backpack, their MetaMask. You need to call this function and only then will backpack open a pop-up and let you connect. If you select cancel here, then the control reaches here, the control never reaches here, which means all this logic only runs if the user is connected. If the user does not connect, you can't ask them for transaction approval, all these things. MetaMask has that code, backpack has that code. Only if the user approves the website, does that website get access to ask for approvals, which is why the first time you connect to backpack, it will tell you, okay, you are connecting to this website and this website will now have access to ask for approvals. It still doesn't automatically have the access to debit your account, but it can ask for approvals. What does that mean? We'll come to very soon. Cool. I've connected it. That's what this line does. What happens if the user connects? We create a Web3 instance, which is nothing. It's just new Web3 window.ethereum. We give to the global Web3 library, which is the thing I put in index.html, this Ethereum variable, the proxy that you just saw, that MetaMask or backpack injects, and we set that as the Web3 variable here so that it can be reused throughout the app. The other thing, very important thing we do is const contract course instance equal to Web3 instance, which is this thing right here, .eth.contract, and we send in the ABI and the address of the contract. Where does this ABI come from? When we were deploying it via Remix, we got the ABI, I put it in a file. Contract address, now that we've deployed our contract, we know it's a string. Earlier I had deployed it here, now we've changed it, so I'm going to replace this with the actual contract address. Finally, we do something here. This is the most important bit. Until now, we're just bootstrapping the course instance and connecting to a contract. Here is when we actually call a function on the contract. We do course instance.methods.coursefee.call, get back the fee, and we set that as a variable. This is the function call that actually sets this course fee variable. And this is how this gets rendered. For my previous contract, this was the course fee. For my new contract, the course fee 0.0035. So let's try to replace the contract in my code. So if I go to app.tsx here and replace this contract address with the contract we just deployed, and I save this. If I refresh now, it says course fees 0.035 ETH. So this logic is what gets set from the contract and sets it as a state variable, which is what gets rendered. And we get Web3 and course contract as state variables, which we propagate down to the two routes that we have, which is the admin route and the normal index route. Cool. We're yet to see what happens in here, but hopefully it is clear how this comes from and how you can connect to a contract, connect to MetaMask and make function calls. Which function call did we make? This function call right here. Where is this function? If I go to my Solidity contract, you can see a course fee function, right? Oh, it's not a function. It's just a public variable, which is the same thing. You can get a public variable. You can also get like call functions. We'll see very soon, very similar syntax. The thing that we got right now was this public course fee function. Sorry, not function, state variable, where right here. How? Like this. Cool. All right. Hopefully this is clear and we understand this bit. The most important bit that's left now is what happens when the person clicks on pay for course. How does their email and 0.0535 ETH reach the contract? How does this open up? How do they get asked for approval? So on and so forth. Now, do I have 0.035 ETH? I don't. So unfortunately, if I do this, this will not work because I don't have enough ETH. Let's try it and then I'll revert to the existing contract, which has like very small ETH requirements. Cool. Let me put an email here. Let's actually first look at the code. So the two sort of components to look at. The first one is course registration. Here you will see a function called pay for course where all the magic happens. When the person clicks on the button, we get their account. So web3.eth.get accounts gives all their MetaMask accounts, specifically an array of accounts if you've connected to multiple wallets. I'm just connected to one, or we assume that the user is just connected to one. And accounts of 0 contains the public key of that account. I repeat, the web3 variable has the window.ethereum variable inside it, where when we were in app.tsx, as you can see, web3 instance is new web3 window.ethereum. That is why this web3 variable that's propagated down has access to the accounts in MetaMask, and specifically accounts of 0 is the current public key of the user that's open in MetaMask. So if the user comes here and connects, this public key that's here is what comes here in accounts of 0. The other important thing is the person needs to pay 0.0035 or course fee amount of fee, and only then will the contract succeed, else the contract call will fail. That's exactly what we do here. So this is the value that's being sent in the function call that we're making. This is from where this function call is being made, and this is the function name, pay for course. Where does this come from? From our Solidity contract. So we're calling contract.methods.pay for course. We're sending in the inputs, which in our case was just the email, and then we call .send with from and the value, and then it's simply if the transaction hash comes back, which means it was successful, you can just track this hash on Ether, the website etherscan.io. If there is some error, control reaches here, and when the final transaction is successful, a final receipt comes here. It has been confirmed on the blockchain. Cool. Finally, these are just buttons. Finally, the most important one is pay for course. When you click on this button, this function gets called, and this is just the input box. Cool. Let's see this in action. Gmail.com, pay for course. When you click on this button, you see an approval. Now it says we were not able to estimate gas. There might be an error, and you see all of this because we're trying to send 0.0035 ETH, but this account does not have as much ETH. So even if I confirm this transaction, it will fail. It actually does say you don't have enough ETH in your account, so this transaction will fail. So just for the purpose of this video right now, I'm going to revert to my existing contract, which looks exactly the same. Only the requirement for ETH over there is much smaller. So let me go here. Let me go back to app.tsx, sorry, right here. and replace this contract back with the original contract that I have. I'm going to save it, and if I refresh, now this contract says the requirement is much smaller. harkiyat2@gmail.com, pay for course, approval. Now things look much better. It says you have to pay. It is 0 ETH because it's so small, but it's actually 0.000011 ETH. And then some gas I have to pay. I click on confirm. And then in the console, maybe I see the transaction hash and the receipt. So this is the transaction hash. I can actually go to Etherscan, specifically the Glory Etherscan, because that's where I've deployed it. And here, as you can see, it's still sort of pending because the transaction is being processed by the Ethereum network, which takes very long. Whenever this succeeds, you should be good to go. I have already made one such transaction before I started the video. As you can see, seems like it happened. I got the block hash, the block number, which block this specific transaction got added to, so on and so forth. Now, if I go to the /admin route, which is fairly simple, it just hits one of these functions. Which functions? It hits this function at the very bottom called get all payments, and it gets all the payments that have been made until yet, which is basically this payments array. And it shows it right here. So I made this transaction a few minutes ago, and then right now I made this transaction. It says total 2 people have bought the course. What happens inside this /admin component? It's fairly straightforward. If I go here to admin.tsx, you will see when both Web3 and course contract have been initialized. Now this is some React stuff that might be obvious to some, not to others. The whole idea is Web3 and course contract get set asynchronously. So we check whenever both of these get set, we call init, and init simply does a contract.method.getAllPayments, which is the function that we were seeing in Solidity. Once we get it, we set it as a state variable, and then finally render it. Cool. So hopefully this is straightforward, and we understand the front end part as well. The last thing that's left now is the centralized backend. People will come here, people will pay for it, people will be like, okay, done. But people will then go to the website and expect them to have course access. They would expect when they go here, click on login and log in and sign up. And once they get into the website, they should already have the access to the course because they've already paid for it here. But right now we have not done any magic to put things here in the course. For that, we need to start listening to the contract. If you go to the contract, you will see anytime a payment is made, we emit an event, specifically the payment received event. We need to write backend code that's always watching this contract, and anytime a payment is made, we need to call a webhook for this website that actually adds the user in the backend. Now, how does this happen is a totally different thing. This is like an outsourced website. It has an admin dashboard. It gives you a webhook there. You can simply hit that webhook with some user's ID and they get added to the course. So that part we don't have to worry about. That will be a black box. The important thing we need to worry about is how you listen to a contract, basically are listening to events on a contract. Whenever this contract is hit, how do you get the person who has actually bought the course and then call the thing on your centralized backend. All right. One thing to note here is there's no sort of real concept of refunds on ETH. If this is an ETH transaction that was done, if someone sends 0.035 ETH to the contract, it's there forever. They can't ask for a refund unless they go to a manual process or like ping me and then I actually send it to them. There's whatever happens on the blockchain happens, and then there's no way to revert it unless you involve humans and someone actually returns it to you. They're good. So be very careful when you're interacting. And this is also why in our centralized backend, we can simply be sure whenever the event has been emitted, we're good to go. We can add them to the course. No chance in hell they can ask for a refund and then we'll have to go and remove them. That does not happen. On the blockchain, everything is final, which is why once the event is emitted on the contract, we can simply add them to the course. Question is, how do you do that? Now I have created a simple Node.js backend. This file right here. So again, there is an abi.ts file which contains the ABI for our contract. Our contract has changed a bit, I think. So let me copy the new ABI and paste it here. I could be wrong. It might not have changed, but just to be sure. And then finally, let's look at the code. It's just 20 lines of code. We get Web3 from web3.js, which is the same library in React that I put in index.html. Here I am importing it as a module. I get ABI from the other file. And similar to how I had initialized the Web3 variable there, I am initializing the Web3 variable here. Now here, there is no concept of a provider. This is running in the backend. Backends don't have MetaMask. Backends don't have Backpack. Backends simply have the private key. Right now, since I'm calling a public function, I don't have to worry about a wallet here. if I had to make a transaction from here, for example, if I want to make the transaction, anytime someone puts some money in my code, I pull it out as well using the withdraw function. Then I'd have to create a variable here called public key and then even the private key. And I had to make the call to actually call the withdraw function, because the withdraw function is gated and requires a signature. But the contract call that we're meeting, or like we're just listening on events, which one are free. You can listen to events on any blockchain, specifically any contract. And two, don't require you to sign any transaction, which is why I don't need a public key, I don't need a private key. I only need the contract that I want to listen to and this other thing right here. Now this other thing is sort of important. It's basically what's called an RPC URL. So there are a bunch of blockchains all around the world. Specifically, if there is ETH has a bunch of miners all around the world. And these miners sort of hold the state of Ethereum at this current point, and these are where an event is being emitted. For your computer, my centralized backend, let's say, to be able to connect here, I need the address of an Ethereum miner, let's say. Like theoretically, I need to be connected to one such miners, which will tell me, bro, an event has been emitted. For doing this, you can either put your own miner here and then connect to that miner, or a bunch of very big companies do this as a service. Very important sort of use case / very big money making machine in Ethereum Solana is become what's called an RPC provider, which means these guys put their nodes in the Ethereum network and give you URLs to connect to them, then charge you based on how many calls you are making. We are using one such provider called Alchemy, which is why you see sort of a connection URL here. You can simply sign up on Alchemy and ask for an Ethereum RPC URL and it will give it to you. So if I go quickly show you my Alchemy dashboard, how are we doing on the battery? 7%, cutting it close. After you sign up on Alchemy, it will let you create an app. So if you go to apps and click on create a new app, it will let you create an app for Ethereum Solana, which you can theoretically think of. They're putting a miner up for you. They're not really putting it. It's a shared resource. The good thing is now they will give you, if I go here and click on view key, they'll give you these URLs that you can get. And then these URLs that are what let you connect to the Ethereum blockchain and listen on events. That's where I got this WebSocket URL from. You can get it as well. Once you do, the only thing we're doing is after we create this contract variable, contract.events.payment received, the event we want to listen to, where does this come from? Again, this comes from the ABI. The ABI is how the types here are right. The types here are actually not right. I've put a big TS ignore here, which if I remove, there's a big error. Please fix it. Create a PR, maybe take some bounty, $30, $50. $50 bounty, who can figure out why this is complaining. And maybe there's no fix. Maybe this is just an archaic library, but I'm assuming there would be a fix, and you can figure out types based on the ABI. So try to figure it out. What is happening? Whenever this event is emitted, do something. I am just logging something here. Ideally, I will, when I deploy this on AWS, eventually, I will hit my webhook that will actually add the user to the course, which is why I will send their email as an input to a webhook URL, which webhook URL is fairly secure. I'll also send some headers here so that no one on the internet can call it. There is some secret header here that goes in that call as well. And that is how my centralized backend will tell my course selling backend, okay, please add this user. They have already paid the Ethereum on the Ethereum blockchain. How does this centralized backend know? They are listening to payment received, and this will only be triggered if the contract has been interacted with and someone has actually paid for the ETH, right here. So only if the control has been reached here does the emit happen, which means someone has actually paid the right amount, which means we can add them to the course. That's exactly what's happening here. From block 0 is a good sort of input here. This basically means it will start from the 0th block on the blockchain, which is when the blockchain started, and look for all the events that happened since, which is why if I run node in cd part 5 centralized backend and tsc to compile it and node index.js, it gives me a big Axios error. So let me just comment that out because this URL isn't really valid. And if I run it again, I should see log for 2 users because 2 users have bought the course. I only see 1 here, but we did buy it for another user. Just want to make sure the contract is the right one. Might not be. Let's see, app.tsx. It's a different contract. I've deployed a few contracts here. Let's build it again. So this is the contract that had 0.000001 ETH. And this contract 2 people have paid for. So hopefully I see 2 emails here. And we do. So this will now keep running. If I don't stop this will keep running and keep watching. Of course, if when I shut my machine down, it will go down, which is why you should actually deploy this on the internet somewhere on an AWS machine. That way you're always listening to this event and adding people to your course. Cool. 4% battery. Before we leave, I want to deploy this contract on Ethereum mainnet as well. So let's do that really quickly. And hopefully, let me just also, we're risky people. We're going to risk it. So this is my Ethereum account. It has $151 or like 0.0814 ETH, which I hope is enough. Compile the contract, go here, maybe refresh. Go to our files, contract, select the right one, go to our compilation, compile, go here, select injected provider, and I've already changed that to Ethereum mainnet here, which is why when I click on deploy with, oh my god, 35 followed by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It asks me a few things. Are you sure you're deploying it on the mainnet? I'm like, yeah, we are too rich, so we will do it. And we'll be paying $60 in gas to deploy it. I don't think it's worth it, frankly. But like one course is like $75 and it's like $60 for gas. If I click on this button, it's done. Chalo, tum bhi kya yaad rakhoge? Don't feel great about this. But this is why like people say Ethereum is bad, it's expensive, it's cheaper to do on other blockchains. That is true. My $151 is down to $91 and I've deployed our contract on Ethereum mainnet now. So now if anyone pays for it and if my AWS machine is running, they will actually get added to the course as long as I'm hitting the right webhook. So you can actually send me ETH and I can withdraw ETH, so on and so forth. This is the transaction signature, which I'm happy to put. That was like $5,000 right there in Indian rupees, which I don't feel great about, but it's fine. Let me charge now. All right. Let's see. So all in all, what did we learn from all of this? Let me just change the view here. Yeah. So what did we learn? Oh, there's a delay. Never mind. So what did we learn from all of this? This whole video has now taught us, let's do a quick summary. 1, pencil died, guys. It has taught us one, Solidity, the first 4 modules. 2, deploying your own contract, the 5th module. Creating front ends. Oh shoot, I wasn't recording the screen. There you go. Creating front ends, and then finally creating backends that listen to your blockchain. All right, so this is what we have learned today. Hopefully this was clear. I know it was a lot of videos and really long hours. What we'll be doing from now is like the next few videos, or like the next one specifically is going to be looking at a bunch of contracts. You now understand how to deploy contracts, fairly simple. The difficult bit is how you write contracts. In the real world, you don't deploy contracts as often. You mostly write the logic for the contract. That's where the moat of everything is. If something breaks there, you're screwed because it's a lot of money that's handling there. So be very careful. we have to be very careful when we write contracts, which is why we'll read through a lot of good big contracts which are deployed on the internet, and billions of dollars have been, not billions, millions of dollars have been stored there. So that way, we understand some mathematical things, like most use cases in